Yeah.
Okay, so it depolarizes through the gap junctions, right? I was going to ask what junctions, but it depolarizes through these gap junctions, and they have these ion channels that once they go to hyperpolarization, right, then they open. And what are those channels called? Or what is the current called? It's like the type of current.
Funny current.
Funny current. Okay, so this is what this chart is. Okay, this chart is basically showing you how the nodal cells reach the action potential and depolarize, descend the gap junctions, or through gap junctions, the entire electroconduction circuit, and the nodal cells cause the myocytes or contractile cells to contract. Okay, and we'll do that again. We're gonna do this and then we're gonna do that. Okay, because she reiterated it, so I know she's gonna ask a question on it. So here, okay, we don't need to know basically this part. You don't need to know the voltages or anything like that, but do know that so when it reaches a hyperpolarized state, right, of the cell, then this funny current will open. And the why it's called funny is because it opens in hyperpolarization. And most channels open because they're depolarized or whatever. Okay. Or because of neurotransmitter. But then okay, sorry. Okay. So they open in hyperpolarization, right? And things can affect the funny current. Okay. And these things would be certain neurotransmitters. Okay. So it could be epinephrine, non-epinephrine, or acetylcholine. So based off what she said last week and what we know, acetylcholine does what? It's a part of what system?
Stops the heart. So the
It's
acetylcholine,
the parasympathetic.
yeah, it closes sodium channels and it closes calcium channels.
Yes. So how does the acetylcholine affect these channels is because it basically doesn't allow them to open, and it basically prolongs the phase 4 right here. You see how it says 4? It prolongs the phase 4 and makes it longer so that the heartbeat is slowed, or the rate in which the action potential is fired, right, and through gap junctions, right, and depolarizes and contracts the heart. Okay, so so when we're talking about epinephrine and norepinephrine, what are they a part of? Are they part of the sympathetic or the parasympathetic?
Sympathetic.
The sympathetic. And so based off of that, what do you think it does to this phase 4? Do you think it shortens it or elongates it or makes it longer? Shortens it, because by shortening the phase 4, it basically makes it contracts the heart faster because it depolarizes via these gap junctions more rapidly. Like the frequency increases, right? When we talked about frequency, it increases the frequency of the depolarization of the nodal cells, which spreads across the gap junctions. If I confused you, I'm very sorry.
Can you just repeat what you said before, like in the way beginning, the bundle of his and all that stuff? Like, where does that come in with this?
Yeah, so we're talking about the SA node, the nodal cells. This is specifically talking about the nodal cells in the SA node. The SA node is the first part, and it's called the pacemaker because it depolarizes at a quicker rate than all the other branch or bundle. They're called, basically they're bundles of nodal cells, and they'll depolarize but much slower than the SA node. And because the SA node does it faster, it spreads via the gap junctions and depolarizes through this circuit, basically. And the circuit goes from the SA node to the AV node to the bundle of his, to the bundle branches, and then to the Purkinje fibers. And when we're talking about the SA node is located in the right atrium, in like a little like subset. It's like right there, right? And so what do you think that would happen first? Like if it's depolarizing via gap junctions, what would contract first if it is located in the right atrium?
The atrium.
The atria, perfect. So if you just think about it like that, know where it's located, and know that the SA node is in that spot, it depolarizes, it contracts the atria first, okay? And that's why that's the first step, right? Contraction of the atria, right? And once the atria contracts, it pushes the rest of the blood into the ventricles. The ventricles are full, the AV node, or not the AV node, the AV valve shuts, right? And once the ventricles start to contract, the ventricles contract, they have all the blood that they need, right? And then they push it along. Now, the ventricles, right? When you think about the heart, right? It's like kind of like in a heart. The atria are up here, then the ventricles are down here, right? And the thing. The Purkinje fibers are the ones to push the blood and basically are the ones to contract the ventricles.
I have a
You
question.
got me?
Mm-hmm.
Yeah.
You didn't lose me, but I'm just confused over the word depolarization simply because when we were just talking to her, somebody said something about it being like technically being it contracting, and she said, don't think about it that way. So now I'm like, what?
Yeah, so no, I was just giving you, so yes, so don't think about when you're talking about the P wave and the all this stuff, think about this depolarization, hyperpolarization, and that kind of thing. I'm just using contraction based off of like the notes and what she put as when the SA node depolarizes, the first thing to contract are the atria, and you can see that on the AKG.
So is it a contraction or is it like a electrical impulse? Like that's why I'm confused.
It's an electrical current that will eventually cause the atria to contract. It doesn't directly do it, but eventually the electrical current will cause it to.
So after like the depolarization kind of happens.
Yes.
Contraction.
Yes, because via the gap junctions, what these nodal cells are doing is spreading the spreading the depolarization to the specific contractile cells that do contract the heart. You got me? So that's why I'm saying, I'm sorry, I'm confusing you. I'm sorry.
No, it's
No, you're not. It's just that simple word depolarization. Like it could really mess somebody up if you don't know. Like
that and then I was like, oh, is that contracting? She's like, don't think like that it is gonna come, but don't think that just because it's depolarizing it means that's contracting. That happens and then contracting happens. But it's okay.
Just like remember when you're thinking of the QRS complex, you're thinking of like electrical activity, like an electrical current.
Yeah.
That's what you have to remember, like the P wave and all that stuff, that's all electrical activity. So when you think of depolarization or repolarization or hyperpolarization, technically speaking, like Olivia was saying, it's not going to be an actual like contracting. It's going to send that electrical current, and then the contractile cells will contract those regions.
Mm-hmm.
So that I was just trying to explain it in the way of the SA node, the AV node, the bundle of his, and through the bundle branches to the Purkinje fibers, and where they're located is basically where they send the depolarization, like in that area. So that's why I talked about how the SA node is located in the right atrium. So you could kind of think about that if she ever asked you, does the SA node depolarize the area in the atria? And they do. If she ever asked that. So they wouldn't contract it, but it would send the depolarization to the contractile cells and they would in turn contract. Okay. All right. So let's go through this. So then we talked about the funding current, right? And then there's the T-type calcium channels, which also open and push to depolarize the cell to threshold even further. Okay. And once the cell reaches threshold, what channels open?
Voltage gated calcium channels and then sodium channels.
Yes. So the sodium channels, no. So it doesn't open sodium channels in this one, but it does open in contractile cells. The first ones to open are the voltage gated sodium channels, and those immediately rapidly depolarize the cell so that the calcium, I will explain that too. I don't want to confuse the two different things, because I just want to be specific that this graph right here is this is the nodal cells. It's not the contractile cells, because they're two different. They have two different systems, or two different like ion channels and all this stuff. Okay, so they're two different ones. And so the calcium, the voltage gated calcium channels basically start to rapidly depolarize the cell to the action potential. And via these gap junctions, this is when the depolarization through the gap junctions happen down the circuit, right? The conduction circuit. And the depolarization moves to the contractile cells, and they in turn are responsible for contraction. Okay, this is dealing with electrical. So after it hits the action potential, it says it's like approximately positive 20 millivolts. It doesn't really show here, but then the voltage gated channels, will they stay open or will they close?
Close.
They'll close, right? And it shows that they're slow to close, I'm guessing. I don't know, because it like ends a little bit after the peak, but she just said that it ends at the peak. And then what channels will open?
Potassium.
The potassium channels, and the potassium channels will repolarize the cell, and then it will go back under threshold. And once it says -60, once it basically reaches the lowest state in which it can, then the hyperpolarization will happen, and what current will open?
The funny current.
Funny current again.
The funny current, and it will allow sodium. Well, so I guess that's what you meant earlier. This is a sodium channel. It allows sodium inside the cell, but it does close about threshold. It does, because once the voltage gated calcium channels open, that's when it just rapidly depolarizes the cell, and the calcium, the T type ones, and the funny current will close at that point. But I think that's what you're saying, Jocelyn. I'm sorry, I just didn't realize. Okay. All right. So does anybody have any questions about this graph?
We're still gonna go, like later on, like we'll go over again like the SA node to like the
Yes, 100%.
Purkinje fibers. Okay, because that's still a little iffy.
Yeah, we learned that last time. We'll go over that.
Okay, good. Just want to make sure.
Okay, so this is just showing you the effect of the sympathetic nervous system on the rate of, or the frequency of these action potentials, and it will become increasingly more rapid as the norepinephrine or the epinephrine it helps opens the T-type calcium channels and the funny current channels even more, and basically allows more depolarization of the cell and gets it faster to threshold, basically. And this is just showing you the different ones. So going off, so this would be like unaffected, right? B would be what? Affected by which neurotransmitter?
Epinephrine and norepinephrine.
Yeah, and C would be affected by what?
Acetylcholine.
Perfect. Okay.
Oh, it's right there.
I think we did this last week, did we? I see marks.
Yeah, I think we did.
Yeah.
I think so. Yeah, we did it.
Yeah. Okay, so this is just saying that once cells repolarize, then during the hyperpolarization portion, the funny current will open, and it says new pacemaker potential. I'm guessing that I don't know what that means, but the SA node will fire, impulse spreads throughout the atria, so the electrical impulse will spread through, or the rapid depolarization will spread throughout the atria, and that will spread to the contractile cells. And via those contractile cells, then it will cause atrial contraction. And next, it will arrive at the another nodal area. And the next nodal area is called the AV node. And the AV node will fire, right? And it will pass it through the next one, which is called the bundle of His. Through the bundle of His, then it goes through the bundle branches to the Purkinje fibers and causes the ventricles to contract. Well, it will spread the electrical and it will basically depolarize the contractile cells and they will make the ventricles contract. If that's more, probably that's more correct.
That's when they said that the SA node doesn't work. So what happens? The AV node gets the signal, hey, this is not working. We have to make the ventricles to contract. It goes to the bundle of His, to the branches, and then to the right and left ventricle. And since we have 80% of the blood coming from the atria, just because when it's full, it automatically will open it. And 20%, that's why we could still contract the ventricles, even though the pacemaker is not working.
Yes.
It happens slowly though, because the other one is the SA node.
And once this happens, or once the AV node or the SA node is deemed unfit or can't fire the action potential anymore, it's not working, or the nodal cells aren't working, then it will then the AV node is the next fastest to depolarize. So, and that's called, once that happens, it's called an ectopic foci. So when a different part of the heart is sending or spreading the action potentials or the depolarization, that's called an ectopic foci. So if the SA node is doing it, it's not called that. But if the SA node's not doing that, it's either the AV node or the Purkinje fibers, then that would be called an ectopic foci. So it will spread to the next fastest area. So it says right here, it says if the AV node does it, it's a rate about 50 to 60 beats per minute. Okay. And if the ventricles do it, or the Purkinje fibers, it would be about 20 to 40 beats per minute. And that's very slow. And it's an emergency. So that's why, because it spontaneously depolarizes, but it just does it at a slower rate. So it's not normally the ones that have the responsibility to contract or to send the depolarization through the contractile cells for them to contract.
Causing our heart to rate to be slower, like slower heartbeat, right?
Mm-hmm. Yes, and it will be slower because the SA node is a normal rate, which for depending on what your like normal rate is, like mine could be 73, Morgan's could be 84, just depending on how much acetylcholine is basically like what we're doing and what neurotransmitters are affecting it. Okay, so this is talking about the myocardial action potential, or the you know, I'm talking about the contractile cells. So how they depolarize and how do they fire action potential so that the cells can contract or the muscles can contract. Okay, so this is, I don't like that graph, but I guess I'm gonna have to use it. Okay, I like this one, I guess. It's better. Okay, so somebody said last time, like, aren't the potassium channels are open the entire time? Yes, they are. Because you can see right here, potassium, potassium, potassium. It's basically the entire time. So just keep that in mind when you're doing it. But it doesn't really particularly matter. Only in this part it does, like right here, 1 through 4. Which is basically the whole time, because 4 is just over here anyways. Okay, so it just kind of sits at negative 85 millivolts. It's the resting membrane potential, kind of sits there, chills out, and waits for the action potential to be fired so it can depolarize from the nodal cells to depolarize to these myocytes. And once the myocytes get this electrical current, right, or the depolarization, then it basically opens these sodium ion channels, right, and they rapidly depolarize, right, until it hits the action potential. Once it hits action potential, then the L-type calcium channels, right, will open, and so will the potassium channels. That's why it kind of stays at an even keel for the most part. And what the calcium channels are doing, they're coming in, the calcium's coming in to the cell, or into the, what are they called? The T tubules or something, into the T tubules down, so that they can basically activate or slide the door up on the sarcoplasmic reticulum. And when they do that, then the calcium will rush out and bind to these tropin. And yeah, you know, I don't know how to say it. And what they do is basically move it so that the actin and myosin can contract and, you know, go like this. And then that's what muscle contraction, how that happens. That was probably the most butchered way how to say it ever, but that's what it's doing. Okay. And that's how we have contraction, because of these myocytes. And, you know, that's good. So once its job is done, right, then basically the calcium channels will close. And once the calcium channel close, obviously the potassium channels will stay open and to repolarize the cell to the resting membrane potential of about negative 85 millivolts. And it will wait there until another action potential is fired, and then it will do it all again.
I had a quick question.
Yeah.
Okay, so at phase 4, when you have like the hyperpolarization and the funny current like opens, so I wrote here that it like waits for the signal from nodal cells to cause the depolarization. Where do the contractile cells like come into play there?
So once so when we're talking about it kind of goes like this, and then it goes
Right.
where,
Mm-hmm.
And it goes up, and
Yeah.
then once there's voltage gated calcium channels. Once those voltage gated calcium channels open, it causes the depolarization via the gap junctions.
Yeah.
Basically through the electrical circuit.
Mm-hmm.
And once that happens, then it triggers this.
Okay.
Yeah, to happen. So basically once that occurs, then this can occur.
Once the depolarization, the impulse occurs.
Yes.
Okay.
Occurs in the voltage or in the nodal cells. Then
Right.
that spreads the electrical current basically and activates or like opens the sodium channels basically via the depolarization, and just it shoots up.
Right. Okay.
Yeah. So basically, if I answered your question, I hope I answered your question. Yeah. Okay. Alrighty, guys. Well, that's so much fun. Does anyone have any other questions? No. Okay. So she said that we don't have to talk about that, but honestly, if you think about it, sodium, if you're blocking sodium, this would lead to like a longer R, or not R, 4, because, blocking sodium, it basically makes I don't know, but I don't know anything. So honestly, if you think about what it says, you could kind of like see like potassium channel blockers that might, repolarize or take longer to, I don't know, prolong the action potential. It says it right there. Perfect. That's so, well, it says the answer, but that kind of sucks. I didn't really understand this question first, but it said, yeah, we're not even going to talk about that. Interesting. We'll probably learn about that in farm. She said that we would anyways. Okay, so this is basically talking about the pulse or the conducting tissues of the heart, or the impulse, the electrical impulse through the heart. So let's go through it together. So the first one is the
SA node.
And the second one is the
AV
node.
And the third one is like the bundle. What is that called?
Bundle of His.
And then it goes through the
branches.
And it's branches on the fibers, left and right.
And down the branches, and then to the Purkinje fibers. And it's really fast. To know here,
Like, so where exactly is the SA node again in the
it's in the in the right atrium. I don't.
It's at the
I don't-
top of the right atrium. Like,
okay.
if this
Oh
is
yeah, I remember the
right
picture.
atrium, it's like
Okay.
right here.
Yeah.
It's gonna be that one right on top, right
That's
there.
like literally like
Gotcha.
I'm in the atrium. It's like right here.
Okay. Got it.
That's the one on top.
And then the AV node is like where
I
is it?
really don't know how
The
to.
AV valve,
Okay.
It would be this one right.
right above the AV valve.
Got
If
it.
this one doesn't work, this one works. It goes in the middle. That's the bundle of His. It goes left and right, and that's the Purkinje fibers that
Mhm.
are gonna squeeze the blood out of the ventricles, like make them.
The bundle of His is right at the bottom of the interatrial septum.
Okay.
We have the atrial septum, which divides the two atriums, and then you have your ventricular septum. Just remember that the bundle of His is right there at the bottom of the septum that divides both atria.
Okay.
So it's gonna be like right there. It's like a little bundle, and then it'll branch off on like that to the.
I don't think he's gonna ask us like specific, but it's good to know.
Yeah, it's good to know, just so like you can picture it in your head.
Right. Okay. Thank you.
Yeah, I like that. I'll remember. I'll remember. So the SA node basically sends the impulse and then it reaches the AV node. And what she did say when she talked about this is that it's held up momentarily to allow for ventricular filling to complete. So basically it like stops it from like sending it super duper fast to the bundle of His down into the bundle branches into the Purkinje fibers, because if that's really fast and that happens like in an instant, then the basically the ventricles won't be done filling, right? Because the atria just contracted after the, it takes a minute, like not a minute, but it takes like a couple seconds for this to happen. That's why you have that's why there's like the P wave, then the QRS, then the T wave. If it all happens so like condensed, then it wouldn't go all the blood wouldn't make it through the heart, you know what I'm saying? I guess. So yeah, I know you're so excited. Me too. Okay. Does anyone have any questions about this? No? Just want to die like me? Good. Okay. Do you guys want to watch this? I think it's the video about the conduction system. No?
Sure, try to see if we can see it.
Okay. Let's see. Oh, we're not having much luck. Okay. Does anyone know how to click it? No? Well,
I think you have to put it in like PowerPoint view almost, like make it like, because right now I think you're in editing mode. Yeah, there you go.
can you hear it?
Let's take a closer look inside the heart. The yellow objects you see on the left are not nerves. They're actually specialized cardiac muscle cells in the walls of the heart. Their job is to send signals to the rest of the heart muscle and cause a contraction. Together, this group of cells is called the cardiac conduction system. The main components of the cardiac conduction system are the SA node, AV node, bundle of His, bundle branches, and Purkinje fibers. Let's follow a signal through the contraction process. The SA node starts the sequence by causing the atrial muscles to contract. Doctors sometimes call it the anatomical pacemaker. From there, the signal travels to the AV node, through the bundle of His, down the bundle branches, and through the Purkinje fibers, causing the ventricles to contract. This signal creates an electrical current that can be seen on a graph called an electrocardiogram, or EKG. Doctors use an EKG as a way of seeing how well the cardiac conduction system works. Any changes to the EKG can mean serious problems.
Okay. Oh, I think it's going to start the next video. Wait.
That was interesting. Thank you.
All right. Okay. Got it. So this is what Emily was talking about, how the SA node is the top of the right atrium, and then the AV node is at the top of the AV valve, right? Then the atrioventricular bundle, or the bundle of His, is in the interverticular septum.
Yeah, it's at the top of the interventricular septum.
And then down the bundle, or the, excuse me, out down the interventricular septum is the right and the left bundle branches. And once they get down to basically the bottom, or the bottom / sides of the ventricles, those are called the Purkinje fibers. And so the ones that can depolarize are the SA node, the AV node, and the Purkinje fibers. Because she never talked about how the bundle of His or the right and left bundle branches could depolarize. She never said a word about it. So I'm guessing that it can be done in those two places. Oh, I get the questions. Hold it. Okay. Well, that doesn't really help. Okay. All right. So which of the following best describes why the SA node is the pacemaker? One, well, I don't need to read all of them, but which one do you guys think it is?
2.
I mean, take a minute to read it, but
Sorry.
2.
yeah, so it's 2. I know. That's pretty lame. I'm sorry. But yeah, it's 2. Okay, because it depolarizes more than other nodal areas, like faster, at a faster frequency, so that, you know what I mean. Yay, we're all right. Okay. So if the AV node were to take over as the pacemaker, would you expect the heart rate to be faster or slower than normal?
Slower.
Lower.
So, perfect. Alrighty. So fun. Okay, so this is what it's talking. So she was talking about the excitation contraction coupling, which I don't know exactly what the word means, to be honest. But it basically, the calcium, when the calcium binds to the door, or to the sarcoplasmic reticulum, then that door will open and allow the calcium out of the sarcoplasmic reticulum onto the tropin, whatever you want to call it, onto that little junction, and then it will cause those things to move so that the actin and myosin can contract and allow for contraction of said parts of the heart.
It'll cause the tropomyosin to move.
Tropomyosin.
Yeah, so you have like the troponin and the tropomyosin. She said that the calcium will bind to the troponin, and the way that it does that is that the tropomyosin kind of moves out of the way due to the calcium.
When the calcium binds to it, it moves out of the way, letting them to...
Allowing the actin and the myosin to like bind, allowing the head to go, and like allowing the contraction.
Yeah.
Yeah.
Yeah. She said that we're not going to be asked questions.
No, yeah. She said,
yeah, we don't understand.
not really, no.
But it will help if we know how it's done, because then we can better understand certain medications later on that are affected or affect this particular process.
And also, without calcium, muscles cannot contract. So if calcium doesn't bind to it, then active sites and myosin will never be able to get together. So muscles then cannot contract, she said.
Yeah, so this is what she's talking. So this is what she's talking about. The T tubules, the action potential travels down the T tubules, and in the case of the oh my gosh, the cardiac muscle, or the contractile cells, then the calcium travels down and binds to this door and causes it to open. Once it opens, then this calcium floods out, and it basically moves, or it binds to the tropion and basically moves the tropomyosin, right, out of the way so that the myosin and the actin can contract.
Mhm.
If I got that right, woo, buddy. Woohoo! Woohoo, I did it. I'm excited. I know you guys are excited too. All right, so this is what she was talking about. She stated that the heart should never be able to tetanize, and tetanize means constantly contract, because if it does that, then you're dead, basically. So you don't want that. We don't like that. And that never happens. And why that never happens is because we have a long absolute refractory period in the nodal cells. I'm guessing this is talking about the nodal cells. Does anyone know? Does anyone know? No? No?
What
Because I
was
know
that
that
question?
the
Yeah,
beat.
That's
This one.
because it's
Okay.
gonna, the nodal cells is what determines the rate of depolarization. So that's probably gonna be nodal, most likely.
So, I think so, maybe.
Yeah, I think so. Because yeah,
And with the red line, it says contraction. So
right. I mean, measured by
I don't
tension
know.
developed.
Well, let's just, I don't know. I think let's just pay attention to the action, this one, whatever this one is.
The
because
red
I
one
know
is
this one's
the
the
nodal
contractile
cells,
cells.
and then the blue one, the action potential, like that's the same ones that we had before. These ones how the nodal cells act, how we have the voltage gated sodium, and then on the other ones where we have the sodium channels open, so they're putting like one next to the other, so we
Okay.
see
I
the
get what
difference
you're
between
saying.
them.
Yeah, I get what you're saying, Jocelyn. Yeah, so she's just saying that this one is a simulation of what the contractile cells look at like, and this is what the other cells look like the sodium, like the other cells in the body, whether it be the neurons or the wherever we're talking about. So because they're different and they have a longer absolute refractory period to stop the heart from being able to tetanize. All right. So she talked about digitalis. Did she say that we'd be tested on it? But she did say we needed it. Did she say? I think.
No, she just said that that's like supposedly to help for the heart something, but it was questionable because let me see the notes that I have for that. So it says it's questionable treatment because okay, it's a treatment for heart failure that makes the heart contract more forcefully, but
Yes.
calcium causes muscle contraction in heart, makes it contract more forcefully. So I
don't know, but basically digitalis and activates this sodium potassium pump, and sodium builds up inside the cell. And once sodium builds up inside the cell, it needs to get outside the cell because then it's really bad. So we need to get it out. It's not our friend, okay? And so how the cell does this is it activates another pump, or that's used for a different manner, and it's called calcium sodium pump. And instead of putting calcium out of the cell and sodium in the cell, it basically puts sodium out of the cell and calcium in. And by putting more calcium inside the cell, it goes into the sarcoplasmic reticulum. And once this entire thing happens and the calcium binds to the door opens to the sarcoplasmic reticulum, more calcium is binded and allows for more muscle contraction and more forceful contraction. We good on that? I don't think we need to know that. So if you guys just were like, I don't even know what she's talking about, then you're good to go. I think I don't think it matters that much.
So more calcium causes more muscle contractions, basically.
Yes.
But imagine like having that much calcium like being contracted continuously. That's why it's a questionable treatment. Like what will you?
Well, it's more so that the sodium potassium pump is, well, one, inhibiting that is like bad for the entire body, but more so in the fact of that they don't even know that making a weak heart be more forceful with its contraction is good. They don't even know if it's good. They're just kind of like, well, it must be good because it's beating, but it might make the heart even weaker. They don't know. or not be good. We don't know. I don't know. Okay. So this is just showing you what it's doing. Okay, so this says at the top, heart cannot tetanize. That means that it cannot seize up and stop. Like this long refractory period allows for it not to tetanize because it's really bad. We don't want that at all. Okay, so the electrocardiogram, it basically records the heart's electrical activity or electrical impulses through the heart. Okay, so it does not measure how the heart's contracting or anything like that, you know, like she said earlier. Okay, so it produces distinct waves, and the P one is the first. The P wave is the first one, and it's atrial depolarization. That's what it's doing. Okay, so it's depolarizing the atria. The second one's the QRS complex, and that simulates, or that doesn't simulate, but that records the depolarization of the ventricles. And the T wave shows the repolarization of the ventricles.
What's going on during the repolarization of the ventricles?
The repolarization of the ventricles, so about halfway through, after it's repolarized, then the myocytes will relax and it will relax the ventricles and stop contraction of the heart muscle there, or the cardiac muscle.
Does it start to fill the ventricles with blood?
So the isovolumetric relaxation phase, this is right after the semilunar valves close and the ventricles will start to relax. During this period, neither the AV valve door is open or the semilunar valve is open. So
during the relaxation of the ventricle is actually the isovolumetric relaxation, right?
Yeah.
Got it.
The repolarization
of the ventricles, yeah, it's like during
that,
the isovolumetric relaxation.
And that's the T wave.
Yes.
Okay, thank you.
Mindy, did I answer your question? Am I saying your name right?
Mandy.
Yeah, Mandy, you're good.
Did I answer your question?
Can you kind of go over that one more time?
Okay, so just repeat your question one more time so I can say.
So I was asking, like, for ventricular repolarization, are the ventricles filling with blood, like, once they're relaxing?
Okay, so when the ventricles are relaxing, when they start to relax, is at the end of when the semilunar valves close. And once the semilunar valves close, the pressure is still higher in the ventricles than the atria. And because of that, the AV valve is not open, but the ventricles starting to relax. So it's starting to repolarize and basically the stop contraction of the ventricles. And as it lowers, as the pressure lowers, then once the atrial pressure is above the ventricular pressure, then the AV valve will open. So during this period, no, the ventricles are not filling as of yet, but I'm guessing towards the end, they are. Like, you know what I'm saying? Like, it's not, like it's after the middle, then at the very end, then they probably start to fill or something of the sort.
Yeah, it depends on where you are. If you're coming from top, they're relaxing, but they're not open, they're not feeling. But once you have the atrial contraction, or like it's full and then you have the AV valves open, yes, the ventricles will be relaxed. They need to be relaxed to be filled with blood. Otherwise, if they're contracting, that's not gonna open. But that's the same what she's saying. It all depends where you're seeing it from. If it's coming from the closure of the semilunar valves, then it's coming down, but there's nothing going on at that moment because it's higher than the atria. Once it goes a little bit under the pressure of the atria, then that's when atria starts filling with blood, AV valves open, and then ventricles in that moment are relaxing to fill them with more blood that they can.
Okay, so I'm gonna go over that with the graph. I'm gonna like really go into that. Okay, so let me just move this bar, this very stupid bar. Okay. All right. Do I have my marker. What pen color, guys? What are we thinking?
Magenta.
Yep. Magenta? Okay. At least we're not doing black again. All right, so when we're talking about this, these are the myocytes in the ventricles, okay? The myocardial cells in the ventricles, so you can see how this correlates with the QRS complex, okay? And how they're depolarizing, and this allows for ventricular contraction, okay? So she said she doesn't like this graph, that's why I'm going to write on it. She doesn't agree with it. So the P wave, once the cells start to depolarize via the SA node, right? About halfway through, that's when the atria will start to contract. Okay, but not before that. Okay, because it you have to allow milliseconds for the nodal cells to spread the action potential via gap junctions to the contractile cells, and they will release the calcium, or that will go up, and then the calcium will go into the cell, and then it will allow the muscles to contract. So it takes like a milliseconds to start that, okay? But you have to allow for it to happen, right? Before you can say that it's contracting. And that's why she kept saying, like, don't think about it as like once the P wave is when the atria contracts, because that's not necessarily correct. It's like halfway through the P wave. But the P wave signifies basically the SA node firing the action potentials via the nodal cells in the pacemaker of the conduction system. If I made any sense, I hope.
We have the atrial, like halfway of the P wave, we have the atrial depolarization.
Well, the depolarization starts at the beginning of the P wave.
Which means the atria, it's filling with blood, right? When you say depolarization, it's the atria at that moment, what's going on with it? Is it filling with blood?
The atria are not filling with blood. They've already filled. So because like when we're talking about like the chart, so once the atria are starting to contract, or this is starting to happen, they're already filled with blood. So once they contract, they basically twist and squeeze the rest of the blood in through the AV valve into the ventricles. And that's why it only takes a little bit, so that it goes to the AV node, then the AV node spreads it, waits a couple seconds. You see how there's like a little couple seconds right here that is just waiting. The AV valve waits, or AV node waits a little bit, and then sends it through the bundle branches to the ventricles, and the ventricles, the nodal cells depolarize, and that's what the QRS complex is standing for, is the depolarization of the nodal cells, or at the ventricles, or at the Purkinje fibers. Okay, it's showing that. Okay, I hope it makes sense.
So basically, that line that you drew, you're saying that it takes a little bit for the atria to contract. That's what that line means.
Yes.
But the atria depolarizes at the beginning of that P wave.
Yes.
Okay.
100%. Couldn't have said it better myself. I couldn't have said it better. Or you couldn't have said it better. I don't know. I couldn't have said it better myself. Okay. When you can't remember how to talk anymore. Okay, so she said specifically that the ventricles don't start to contract to about the R. So like they don't start to contract until the R. So it says that it's a little bit before, but it's not. She said that it takes a minute, right? It just takes a minute to get there. So that's what this is showing. The myocardial cells in the ventricles, they're starting and they just shoot up as fast as humanly possible, but it takes a minute, right, for those ventricles to contract. Because why? The calcium has to go into the cell, bind to the door, open the door, the calcium floods out, binds the tropin, and then the tropocinogen, or whatever the hell it's called, shifts and then allows for the muscles to contract. So it takes a second, okay? And oh my gosh, I can't believe I have a low battery. No, okay. And then this whole time, it's basically showing that it's contracting. And so it even shows that until the middle of the T wave, it's still contracting, which is true. Because why? Because, it takes a minute, to stop contraction. So in the middle, so then we talk about the T wave, and the T wave is ventricular repolarization. So basically the ventricles or the nodal cells in the ventricles are still starting to repolarize, basically get back to the phase 4, so that they can, once they get to the phase 4, then they can repolarize. So it just shows that it's ventricular relaxation, and this would happen when the semilunar valves close. And please correct me if I did that wrong, because I have a slight feeling I said something wrong in there. Did I? We know. Okay. All right. Let me just think about that for 1 second. Let me make sure I said like the exactly right thing. T waves. Yeah, so the T wave is the relaxation phase, and it takes a second, so that's why it doesn't stop contracting until after. So it just takes a minute to slow down. So I'm guessing that's how when you're going up, and then in the ejection phase it goes up and then starts coming down. So I'm guessing that's when the ventricles are starting to relax, but they take a minute, right? And then once they fall below the aortic pressure, then it closes, and ventricular relaxation starts, and this allows for the repolarization this starts the repolarization of the ventricles, so that another action potential can be fired, and all that stuff, all that jazz. And I'm guessing it also allows for the, it says ventricular diastole, and also, so that it can allow the atria to fill with the ventricles with blood again, and then it can do the process all over again. Did I lose anyone? I feel like
I'm really lost. I just thought I'd throw that out there. I'm having such a hard time correlating everything together. Like everything just kind of seems like I can't make sense of any of this. Like what, like where, I don't know. I'm probably the only one, but
the echocardiogram is measuring the electrical impulse through the electrical conduction circuit. So when we talk about, how we talked about before, the SA node, the AV node, through the bundle of His, through the bundle branches to the Purkinje fibers. And this is basically showing you a roadmap of what is happening with this electrical current. And so you can see right here, the P wave, this stands for depolarizing of the atria. And depolarization of the atria, this is regarding the nodal cells, specifically the nodal cells, okay? Am I right? Does anyone know? Am I right? Am I right or am I wrong?
I think so. I don't even know. I'm going to say yes, you're right.
I don't think it's talking about the contractile cells. I think it's talking about the nodal cells. Okay.
Yeah, because I wrote down that the EKG just is measuring depolarization, not contraction. So it wouldn't be the contractile cells. Okay, so it would have to be the nodal cells.
So it's depolarizing in the atria, which would be the SA node, right? And as it's depolarizing, then it's spreading basically depolarization via gap junctions through the AV node. And the AV node basically is a part of ventricular contraction because of where it is, and that's what it does.
I'm sorry, when you say depolarization, what do you mean? Like, I know that means something is going up. So is like, does the depolarization just mean that it's just spreading, like the electrical signal is spreading?
So when we talk about depolarization, we mean depolarization of the cell or hitting to the action potential.
Okay.
It's getting more positive. It's deep. When she talked about, I'm not even going to go there. Sorry. I was going to go into polarity, but I was going to everyone was going to be like, huh, what the hell are you talking about? Got that 20 years ago, bro. Okay. But it's depolarizing or it's getting more positive. Okay? And once it gets more positive, it fires the action potential and spreads it via the gap junctions to the rest of the nodal cells and the contractile cells, wherever they may be. Okay.
So once we're at the P, it's gonna be the SA node. Once we get into the Q, it's like staying there before getting to the AV node. And then R is still AV node.
I mean, I wouldn't think about it like that. I
No.
wouldn't think about it like that. I would think
Just think about it like once it waits a little bit and then it goes
it waits
back.
a little bit right here.
Yeah.
It waits a little bit so that it can allow for the ventricles to basically gain the last bit of blood, then it will contract.
Okay.
That was probably my bad. I probably explained it a little weird.
No,
Okay.
you're good.
So the P wave signifies depolarization of the atria. Okay. And it takes a minute, so that's why halfway through, then the atria contract. The atria will contract and fill the rest of the blood into the ventricles. In relation to the other graph, once the ventricles fill with the most amount of blood and basically have more pressure than the atria, then the AV valve will close. Once the AV valve closes, then this will be the start of, well, the start of Q, or even more so a little bit before that because it takes a minute, right? So it'd be more R, right? But Q is the depolarization of the cells in the ventricles. Okay, and why it waits a little bit to depolarize the cells in the ventricles via the Purkinje fibers is because the AV valve allows for the ventricles to fill fully, right, before it sends the electrical current signal to the Purkinje fibers to contract, because you want the rest of the blood in the ventricles. Okay, does that make any sense at all, or did I like kill you?
Yeah,
No,
it
that
does
makes
make sense.
sense.
It does. Morgan, did it make sense?
Yeah.
Okay, good. Okay. All right. So once the ventricles start to contract, right, in that contractile phase, relating it to the other graph, it's called the isovolumetric contraction phase. So during that phase, neither the AV valve is open or the SA node. When you talk about weird things, okay, when you go back and forth like 100 times, okay, the semilunar valves are closed too because the ventricular pressure is not above the aortic pressure as of yet. Okay, but it's gaining contraction. So that's about when the ventricles start to contract, that's the R. Okay. In relation to the graph, the Q to the R, basically that's when the cells are starting to depolarize rapidly, and then that whole process will start with the sodium channels will be open and rapidly fill, which is right down here, right? And then basically the calcium will come in and start contraction. Okay. So during this time, right, the ventricles are starting to contract, and once they fully contract and basically reach where the aortic pressure is below ventricular pressure, which is after basically this, then the ejection phase starts, where we'll basically send the blood through the body, right? And then the cells, right, will start to repolarize because the potassium will, repolarize, right? And then it will start to come down. You know what I'm talking about? You know that graph where it starts to come down, starts to go down. And the cells are starting to repolarize, and it's sending the last of the blood, and it's basically relaxing, right? And it doesn't start to relax until about halfway through, but you can see the cells are starting to repolarize. And once that semilunar door shuts, right, then it's fully getting into relaxation stage, and it would be after the T wave. Did I confuse you more?
Are we gonna talk more about like isovolume? My God, the volumetric, like the isovolumetric relaxation and contraction.
Yeah, I think. Yeah, we can. if you want to.
No, because like I just haven't really gone over it, so I was just wondering, because sometimes like we're talking about it and I'm like, wait, I need a minute to think about it.
Yeah. So I do want to, I do want to do the worksheet just so that we can review the last weeks, because I know that some of you have been busy, or like, yeah, you're not here, or you didn't know about it or whatever, and so we'll go through the worksheet. I can kind of explain any questions that you have, and it's like very clear. It helps, because going through the PowerPoint, it's kind of hard to like ask you questions and you think through it in the process, which you do, and like kind of think about it. You know what I'm saying?
Yeah,
So,
exactly.
so we're going to do that if we have time. Hopefully we do. What time is it? We don't know. 9:17. Yeah, we should have plenty of time, to be honest.
Okay.
Okay.
Great, thank you.
No problem. Oh, my magenta. Where does it go? Okay. Oh, lovely. She took this out, and I'm guessing for a good reason. So we're just gonna wait. Okay, so this is what I was talking about before with the P wave and the QRS complex and the T wave. Okay, so just Morgan, I know that you love more note cards because I know you. Okay, but this is like perfect way to learn about it. It's like just think about the P wave, and you can write down atrial depolarization, QRX complex, ventricular depolarization, and T wave, ventricular repolarization. And I'd also put on your, if you put a note card, I put on it halfway through is atrial contraction. Halfway through the QRS complex is contraction. And halfway through the T wave is relaxation of the ventricles. You can kind of do it like that. But just make sure that you have like halfway through, because then you might get confused, thinking that contractions repolarization. It's not, because it's two different things when we're talking about two different types of cell, or not cells, but two different types of functions. One is physical and one is electrical. Oh my gosh, how do I, oh. Okay. So we're not going to talk about that. But this is basically, she said how to tell a normal AKG is everything's pretty much the same and consistently away from one another. Right here, it's pretty that no SA node activity. And this is one of the reasons why I talked about it earlier, about how the SA node repolarizes the atria first. And by depolarizing the atria first, this allows like halfway through for contraction of the atria. And right here, it says no SA node activity. And see how there's no P wave? There would be like a little wave right here. So if you look up here, right here, there's no P wave. So it kind of you could say that because there's no P wave, that there's no SA node activity, because it's not, because it can't go backwards, or it should never go backwards. If it goes backwards, we have problems. Okay. So because it goes from the SA node to the AV node, it never goes back. And if it does, we got problems, heart block, we got like all sorts of crap. We never wanted to go back. I don't even know if it would do it like that. It would just be so messed up. It'd just be like, I don't even know, guys. I don't know anymore. But this, I guess right here, is just showing you that there's a block in the AV node because there's no ventricle contraction. And sometimes it gets through, sometimes it doesn't. Because you see right here, this is normal. So it gets through, but the P wave sends off through the AV node, but it doesn't go anywhere. It just can't even get there because there's a block. I probably confused everybody, but that's...
No, it's good.
And she said this happens pretty regularly. I couldn't tell you, but this is bad. We don't want this. No, 0%. Because ventricular fibrillation means the ventricles are quivering. No bueno. We don't like that. Okay, so this is what I was talking about before. So the absence of the P wave on an EKG would indicate which of the following. And go. Jocelyn remembered last week. Yeah, it was. I'm
Okay,
sorry.
I'm
I only see you. I can now I see me and everyone else. But because I like couldn't see this rest of the screen. But yeah, last week we went like 1, 2, 3. You know, whatever.
If
But
you already know, I was gonna say it before anybody read it. So I'm like,
yeah, so
okay.
it's a problem with the SA node because the SA node is initiating the depolarization of the atria. Okay, and the P wave signifies the atrial depolarization.
So every time they talk about P is SA node, right?
Yeah, I mean, you could say that. Yeah. I felt that.
Oh my God, I didn't realize my mic was
On
on
a
my
level.
side, so
I felt that. Okay.
Struggle is real.
turn off my
Right.
mic.
So, so we're going to talk about this later again, but basically on the AKG, this is when you're hearing the heart sound. So the first heart sound is what?
AV valve closure.
AV valve closure. And when the AV valve closes, what happens?
What happens when it closes? It makes it
After it closes, what happens?
The
Does
first sound,
Like
As-
after the first sound happens, what happens? Like when that AV valve closes, what happens?
so
Ventricular pressure doesn't go above atrial pressure,
It
and
goes
that's
above.
the isovolumetric contraction.
So
yes.
contraction of the ventricles happen. So yeah, so that's why the only reason I wanted to bring that up is because right here, you see how about halfway through, that's when the first heart sound is. You see that? So you see how the first part of the up scale, it's just showing you that the cells are depolarizing and no contraction has happened. But once that AV valve shuts, contraction happens. And once it starts contracting, then this happens at the outside of the RQ.
QRS.
URS, yeah.
When you have the RS. So RS is showing you that the ventricles are contracting and so this signifies the first heart sound. And then the second heart sound is at the end of ventricular repolarization, or like right here, because it takes a while, like I said, to start the relaxation of the ventricles.
Does it take, like, because it takes a moment for the ventricles to relax, does that mean that they're filling back up?
No. So remember how we were talking about earlier? I don't want to confuse anyone. So we'll go back to the chart like later and we'll explain it on the chart. But so if you look at the chart, I don't have a pen. Of course I don't have a pen. You think I'd have a pen anywhere near me? Anyways, okay. So if you have, okay, let's do it like this. So so this starts the ejection phase. Let's just say this is the ejection phase right here. So this is the ejection. So you see how about right here it starts to go down?
Yeah.
Okay, so that's signifying the relaxation of the ventricles, but it's not below aortic pressure yet. So it's still pumping blood out. But it's like the cells are repolarizing, and once it gets below, so you see how so about right here would be basically the ventricles start to relax, like about the middle. But you see how it's like later on, because even though it's relaxing, it's still going down, but it's still above atrial pressure. It's still above aortic pressure. So once it hits that, which is at the end of repolarization right here of the cells, then that sound will happen because the semilunar valve is slamming shut.
Mm-hmm.
Okay.
Did I?
So the T wave is occurring at the end of the ejection phase?
Yes.
Okay.
Because no. The T wave is so it's kind of hard to say because it's like once the ventricles are losing their blood, they're starting to relax, and they're still they're relaxed, but it's like they're depolarizing and or repolarizing, and therefore that after they're relaxing, and but they're still above atrial pressure. You're gonna not atrial,
Oh,
they're
yeah,
still above
that's there.
aortic pressure because they both go down together. And once the aortic pressure stops going down, then it goes below and that semilunar valve slams shut.
Okay.
But then it says right here,
Yeah, shortly after T wave begins.
so like you could just think about the T wave and the heart sound too being like together, because it doesn't really matter exactly when specifically does that heart sound happen, but it does happen when the semilunar valve closes. And you could say that the T wave is a part, like has to do with, not has to do with it, but it's a part of the repolarization of the ventricles, which causes relaxation of the ventricles. And therefore, once the ventricles are relaxed and start to relax, the aortic pressure goes below the below the ventricle pressure, and the semilunar valve will slam shut, but it's still above the atrial pressure, so the AV valve is not open yet.
¿Qué buscas para acá? Si tú tienes ahí cargadora.
I confuse you probably 100%.
It's okay. I just need to go over it like again.
Yeah.
So what I think about the T wave when they mention that, it's probably that it's like the relaxation of the ventricle. That's why it starts relaxing, but it won't close until it reaches the pressure is less than the atrial. So that's what I
The
think.
aortic, yeah, I messed up that like 5 times.
Yeah.
Um,
Probably
yeah.
gonna have to mention it like 10 times.
Yeah.
Yeah.
Yeah. Okay.
Wait, semilunar valve is aortic, AV is atrial.
It's atria to ventricles, and semilunar is aortic or pulmonary to ventricle
Okay.
to ventricles, or vice versa. Like the AV valve is between the atria and the ventricles, so it allows blood to come from the atria to the ventricles, and the semilunar valve allows blood to go into the aorta or into the pulmonary circuit and back, and then it closes. It's like I confused myself, but like ask your question again, maybe I'll be able to help.
No, because sometimes they're both start with A, so I get them confused sometimes. So I was just basically asking, is semilunar aortic, and then
Yes.
is
Yeah.
yeah.
You have a pulmonary semilunar valve on the right side, and then you have a aortic semilunar valve on the left side.
Okay.
And that's basically just like those valves, like whether they're closed or open determines like the ejection phase, I guess, when it's going into the rest of the body. Right?
Yes.
Okay.
Okay, so this is basically showing what I was showing or trying to explain a little bit. I suckedly I did try to explain. So this is showing the like contraction of the ventricles. So when the ventricles start to contract, like at the R, right? Not before, at the R, you know, but this is, it's kind of, I don't want to make anyone confused, but once, because of the depolarization through from the nodal cells to the contractile cells, then once our complex happens, then the myocytes start to contract, and once they start to contract, the ventricle starts to contract. But right before that, the AV valve slams shut. So that's why there'd be a first heart sound right here. Okay. And the T wave, once the cells repolarize, then the ventricles start to relax. Via relaxing, it goes below aortic pressure, and the semilunar valve slams shut, and this causes the second sound. We're good?
Mhm.
Did I confuse anyone?
We're getting there. We're getting there.
We're getting there? Oh my gosh, really?
We're good. I'm good. I'm kidding.
Woo, I love that. Getting there is better. Oh my gosh, we got to the summary. That's amazing. Holy mackerel. Okay. So, what is the pathway? Tell me the pathway of the electrical conduction.
SA node goes to AV node. It goes through the bundle of His. It goes to the branches, to the Purkinje fibers, and then it contracts the ventricles.
Well, that's just saying the spread of the depolarization, and then via the contractile cells, then that would be the contraction. Yes. And okay, so in let's just say my SA node's not working. What in my AV node started taking over? How many beats per minute would my heart approximately beat?
50 to 60.
50 to 60.
And let's just say I had a heart block, right? And the block was it blocked basically the signal from my SA node, and it stopped my AV from sending signals, and basically just can't. Actually, that's probably wrong, but let's just say it like this. Okay, not a heart block. Let's just say my SA node and my AV node stop working completely. What would take over?
The Purkinje fibers.
And what would my heart rate be?
Really low.
I think it's like 40 to
20 to 40.
40 to
I think it's 20 to 40, which is like emergency.
yeah, and it's really bad because you don't want that because your heart basically there's no cardiac output. It's very very little. Okay, so
And then if that happens, it's called ectopic foci or ectopic pacemaker.
yes, relationship. Okay, so let's just say we're talking about the myocardial cells. If we're talking about the cells, the calcium, what do the cells do with the calcium that comes into the cell after the cells hit the action potential? The calcium channels will open, and what happens after that?
Don't they go into like the T tubule?
Yes.
I don't know what happens after that. So the T tubule, and then doesn't it release the calcium?
Yeah.
To
And you don't
grow?
really know like everything, just
Okay.
briefly. Yeah, so it releases the calcium,
Mhm.
and the calcium
Goes into the sarcoplasmic reticulum, or
no,
not?
the calcium comes out of the sarcoplasmic reticulum, and then it goes and binds to these little tropotin, and it moves the tropocinogen, and it allows for muscle contraction. And that's the relationship that the myocardial action potential has with contraction. I don't think she's going to ask that, but it says it on the summary, so I'm just going over it one more time.
So the contractile cell, like that whole action potential that it goes through. So I'm just confused. Like I know what happens when like calcium comes in and that whole thing happens, but that whole process is what actually causes the contraction to happen.
Yes.
Because of the actin and myosin binding together, right?
Not binding, but contracting, like sliding. Yes.
Interacting together.
Interacting. Yeah. Exactly.
Okay. Okay, I just want to make sure.
And
we don't need to know. Sorry, what were you saying, Dawson?
No, I wanted to ask about when they ask about myocardial action potential, that's just focusing on cardiac muscle, or I'm getting that.
It's talking about the myocytes and basically what they're doing and how does that deal with contraction, and that's what we're talking about. How the contractile cells they depolarize rapidly via the sodium channels. Once they hit the action potential, then the calcium channels will open, and the potassium will stay open as well. And the calcium will come into the cell, right? Go through the T tubules and then bind to the door, open the door of the sarcoplasmic reticulum, send the calcium out. The calcium binds to these little things on the troponin, and the tropinogen slides, and then it allows for the actin and myosin to basically slide and contract. And this causes contraction, the myocytes or the contractile cells, but the depolarization of the nodal cells and through the gap junction. This is what causes the action potential to fire in the myocardial sites, or whatever you want to call them. And that's what causes contraction. If that confuses you, I'm sorry.
No, it's good.
You said we don't need to know like the process of like when the calcium goes into the cell, into the T tubule. We don't need to know that. Do we just need to know that the end result is the like muscle contraction and the actin and myosin interacting, and that's what causes it?
Yeah, just know that that's what causes muscle contraction.
Okay.
Or the
So you can't. So we just basically need to know that you need calcium for the contraction of the heart to happen.
yeah, know that. Yeah, 100%.
In the LES session that we had today with her, she said you don't need to know like the steps, like the ones that we've been doing with like the T tubules and the sarcoplasmic. She just said know that calcium is what does the contraction. Like just know that calcium is like what does it. That's it, really.
Great. Love that. I do. That's great. I didn't study the muscle part, because she said that you don't need to know that, but I was just doing it to explain it so that, for later on, maybe it might help someone. I don't know. So the EKG measures what? Does it measure contraction, or does it measure the electrical impulses?
Electrical impulse.
The entire electrical impulse, right?
Perfect, yes. From the atria to the ventricles and so on and so forth. Okay. The P wave. What does the P wave stand for?
Atrial
Depolarized.
Perfect. And the QRS complex stands for what?
Ventricular depolarized.
And the T wave stands for?
Ventricular relaxation.
Nope.
No, repolarization.
Repolarization. There you go. I know it can trip somebody up just like that. I'm gonna bet.
Repolarization. Yeah, that's what I meant to say. And then it's relaxed also, but not at the beginning, right?
Yes.
Okay.
It takes a minute, right? And if she ever asks you a question like, what does the P wave stand for? Atrial relaxation, atrial contraction, atrial repolarization, or atrial depolarization? You would say?
So depolarization.
Yeah, depolarization.
Depolarization. And I'm gonna bet you money that that's gonna be on the test. Like I will, like $5 right now.
Like that, because I'm like.
So it would be repolarization, right?
Depolarization.
Depolarization. Ventricular repolarization is the T wave.
Oh, I thought she said T wave. My bad. And it goes the same for the P wave and the QRS too, right? They contract, but not right away, right?
Yes.
Okay. Thanks.
No problem. Okay, so this is talking about arrhythmias, right? Bradycardia, which would be like below 16 beats per minute, and then tachycardia would be above 100 beats per minute.
Did we skip that?
Talked about it a little bit. I'm sorry.
Did we skip
Yeah, she did. We did that, but she mentioned, like, I tried to catch up on the story because one way or the other, one question of the story always come out. She said the bradycardia was like when someone is in good shape, something like that, or when I don't remember the story that, but
bradycardia is like if you're like an athlete or whatever, like they need more. They need like more cardiac output or something like that, so where they can have like a lower heart rate and it being normal.
Yeah, she mentioned that if you were a swimmer or athlete, stuff like that, But all those two are abnormal, right?
Yeah, no, they're not normal. And also
Not abnormal.
bradycardia could be from an ectopic fauci. I mean, because you can just think about it as if the AV node is firing and the SA node is not working, then the beats per minute might be below. It'd be 60 to 50 beats per minute. So it could be also caused by that. And it also
Okay,
says
wait. I have a question before I keep being confused. I'm sorry.
Yeah.
When we're talking about 60 beats per minute, are we specifically talking about systolic or diastolic pressure or
So the beats per minute is basically the
just the beats?
like per minute, like one, like when you listen to someone's heart, it goes dun 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 dun, like 1, 2, 3, 4, like
Okay.
that.
So it's not talking about diastolic or systolic
I
blood
don't think
pressures.
so.
Okay.
No.
Thank
He's talking
you.
about like the whole thing, like all the things together, like the atrial contraction, or like basically all of it together in one beat, like it's just together. You know what I'm saying? Like on
Perfect.
the
Thank you.
EKG. Yeah. So it says tachycardia can result from an ectopic fauci. It could be from, she explained it, but like I still don't know. But basically, it can, I mean, from my understanding, it could be like from an overactive SA node, like an overexcitatory one, where it could just like keep firing really fast. And that's why it's called, if it's from the atria, that can be a supraventricular tachycardia, and that's what she has, where it can like result, like the SA node is excitatory. And I don't really know past that. Does anybody know? Does anybody like remember?
Yeah,
No,
so
I mean,
A bit confusing because usually isn't like a topic foci when it's lower because that one's not working. So just like her coming up saying that tachycardia it's more than 100 beats per minute and then it could result from an ectopic foci, I'm thinking that the SA node it's not working, so it should be slower. So I guess like we could call ectopic foci different ways. So it's like not only when it's not working, but when it's over working.
I think it's
Yeah,
because
that's what I wrote. I wrote or hyper excitable, like it's just,
Okay,
yeah,
so
it's
that's
just
good.
when it's overexcited or when your AV node isn't working properly. And since your SA node has spontaneous depolarization, it just keeps going and keeps going and keeps going if your AV node like is also not working. So it's just overexcited and keeps like depolarizing and just keeps going like crazy. And then that can cause like it to go up.
Good to know.
Okay.
Because it's the most excitatory one.
Yeah.
That's why it's called the pacemaker.
So she talked about flutter. Atrial flutter is extremely, well, it can be in the atrial ventricles, it says here, but it's extremely rapid, but it's coordinated rates like 1, 2, 3, 4, 5, 6, 7. But they're all coordinated, it's working properly, it's just like really fast. Fibrillation, it's the quivering, whether it be of the ventricles or the atria. There's no coordinated pumping, like it's just not happening right. It's like, have you ever been to like an orchestra or like a band, but like not like one that's professional, because it's usually run super great, but like one of those like middle school ones, I participated in one, and I have to say that, like when which is like off, you know what I'm talking about, like with the percussion's like doing one thing and then the flutes are doing another, like if you know what I'm talking about. That's kind of what it reminds me of, like everyone's trying to work together, but it's just like not working at all. Okay, so that's what it reminds me of. But so the flutter or the extremely rapid rates can lead, especially in the atria, she explained, very quickly to fibrillation, because if it's too rapid, then it can get confused. I don't know, it stops. Like, we don't know. It just stops and quivers. It's like, I don't know what to do anymore. It's just too fast. I don't really know how it does it, but it's just like, fuck. And if VFib's really bad, don't want that. AFib, it's not as bad because again, 80% is automatically filled into the ventricles. and 20% squeezed out, and the 20% it can basically like stay on the sides of the walls, so you can have a predisposition to clots. It can also, so like atrial fibrillation, obviously if you're talking about that, then maybe the SA node is not working as well or not working as all. So if that's the case, then impulses to, if ventricles could also be altered if the SA node isn't working.
So with VFib, since there's no cardiac output and there's just a bunch of blood sitting in the ventricle, could that cause like backflow back into the atria? Right? Because it's just sitting there. But never mind. Because wouldn't the AV valve have to be like open in order for that to happen, like the backflow? Am I just confusing myself?
I don't think you need
I'm just wondering why it's like fatal if it's not.
Oh, because it's not pumping blood to the rest of the body. That's the problem.
Okay.
Because if it's quivering, it just can't do anything. It
Right.
can't contract to send the blood and inject the blood into the aorta. So then it can basically stop the blood from moving to the rest of the body, and if you can die.
Yeah, I don't know if it would cause backflow then, because I don't think the ventricle would be, or the AV.
I don't think the backflow is the biggest problem. I think that it would be the lack of oxygen to the rest of the
body or the organs.
Yeah.
Got it.
And the AFib, it's not immediately life-threatening because remember, 80% of blood does come out, so that's why it's not.
Right. There's only 20% left in the atria, and then once it contracts, then it goes and got it.
And usually, also it does cause backflow because remember, yeah, it's not working, but more blood it's gonna keep on coming from the atria because the atria it is working, so it's gonna be coming more blood. It's gonna cause backflow to the atria, and eventually keep on causing. That's why it's fatal as well.
Got it.
But I don't remember. You explained it to me many times, but I still don't get like the quivers. What was that? Like I know it's like the shaking, but I don't get like the concept of like the quivers.
It's just not.
It's like spasms almost, I guess.
That's like it's like it would have to be with the contractile cells. They're not working. Like they're just not contracting because they're not receiving the signal.
Okay.
There's probably, or they're receiving such a rapid signal that it's like just
confusing.
I'm guessing. Okay, so there's this thing called ventricular tachycardia. Where is it? It's on here. Where is it? I know it's on here. Don't look.
Oh.
Okay, so this right here, VTAC, ventricle tach. So you see how fast it is? So it's the ventricles contracting so fast, and it can quickly degenerate into ventricle fibrillation. Because I'm guessing the signal is like just so messed up, and it's just like there's a picture of it, I'm pretty sure, of like it going in a circle. Where is that one? Like this. And you see how it comes down and then it comes like back around. You see, and it keeps keeps depolarizing the cells at such a rate that they're just like all fucked up. They're just like totally done. You know what I'm saying? Like they're just done. So and this is a we're not going to talk about that, but that's called a circus movement, and that's why I'm guessing, because it says right there. It's because that's what I was talking about, the re-entry, because that's one of the reasons that it could cause it, because it's depolarizing the cells at such a rate that it's like quivering. It doesn't even know what to do anymore. It's like I'm shaking, but I don't know what I'm doing. And so this is what I was talking about before. Atrial flutter, it quickly deteriorates to atrial fibrillation. The ventricles may beat very rapidly or very slowly because it might be the SA node is sending off such strong and fast signals to compensate that it doesn't even know what to do anymore. So it's like it might be really fast or really slow because the AV node is the one that's contracting, or it could be that the Purkinje fibers if it's like a heart block, but usually it would be like the AV node would be the second one. And it responds to some responses, but not all responses. Because there could be a block from like any number of things.
My goodness, it says the ventricular fibrillation, you will be dead within minutes.
Yeah.
So it's like minutes.
Yeah. Because if you're not getting oxygen to your body, causes multi-system organ failure. So your body just dies.
Your brain, mostly your brain.
Your brain will die. Not good. Not good. We say not good. So, so weakens heart if prolonged in the rapid rates, obviously, because if you're beating so fast for such a long time, it can obviously weaken the heart. But it is the heart's job to beat. So it is so complicated. We don't even know anymore, guys. I don't even know, but it does do that. Apparently, it weakens the heart if prolonged at rapid rates, which makes sense. You know. Okay, so ventricular fibrillation, death within minutes, cause circus movements. The book, she said the book talks about it. She doesn't talk about it, but it's not usually possible due to the long refractory period and tetanization and contraction. Because of the long refractory period, it allows for the cells to repolarize and go back and basically fix itself before the next contraction or the next depolarization to happen. But if it doesn't, and there's the wheel of fortune. Okay, the wheel of fortune. Basically, it's showing you that there's damage in the tissue, and apparently on one side of the bundle branches that it can't go back, that instead of, because it's not being sent through, or the signal's not going through, that it comes back around, right? And it depolarizes the cells, or it sends the signal over and over again, and it can basically just mess up the heart very badly. Or the ventricles, because it's basically just depolarizing the ventricles over and over again. And this can cause ventricle fibrillation because it's kind of like, I don't even know what to do anymore, guys. I just don't. It just basically fucks up the entire cells in that, thing. I know, you're so excited. That's what reentry is, or what I was talking about. Okay, so we've been over this, like, I've went through like past the slide like 5 times. So you probably know the answer, but a patient that has atrial flutter with a ventricular rate of 30 beats per minute, which of the following can be concluded?
Maybe no, it's complete.
Number 3. Oh, no, my bad. No, number 2.
Yes, number 2. So the AV node is completely blocked. Because if the AV node is completely blocked, then the Purkinje fibers will start to initiate the action potentials, and it could be between 40 beats per minute or 20 beats per minute. Mm-hmm. Patient's fine. This is a little rest,
Good luck with that.
Bro, oh God.
Wait, so if the AV node is completely blocked, what is that like for the SA node? Does that mean like the SA node, are we saying that the SA node and the AV node are like blocked?
Most likely.
Yeah, so most likely, but it could be like the SA node sending it to the AV node, but the AV node's blocked, so it can't really do anything. So it might be that the atria are contracting or the atria are depolarizing, but it just can't get through. So then the heartbeat's weird. We don't know, but it's probably that the SA node is like messed up as well.
Can you give me the definition of the atrial flutter again? I'm sorry, my iPad died. So I can't.
Okay. Let's go back because I gotta make sure I'm correct. Okay, so
It's a rapid rate.
flutter is extremely rapid but coordinated rates.
Coordinated rate.
So atrial flutter, the beat or the SA node would probably have been shooting off lots and lots of action potentials very fast, but it's not because it's blocked, it's not even doing it. I think there's a picture. It's not even sending them. Okay, so I think it's, is this what it's talking about? Maybe.
Impulses 1, chaotic signal, and then rapid ventricular impulses.
I just feel like
Oh
I'm
yeah.
sorry.
This is what it's talking about for the most part, but this is a little different. So it would be if the beats per minute were longer, right? Like if we're talking about like much longer, because obviously this is pretty fast. I mean, for what we were talking about before, but it would be like the atria are like contracting really fast. So like these little things, like, but then it will wait, but then it will be for a while, right? And then eventually it will get through the atria and contract. But in the case of it being completely blocked, then the Purkinje fibers are the ones that initiate contraction of the ventricles. So then you get a lot of this stuff, but then only few ventricular contractions. And that's really bad because we need the ventricles to contract or we don't get enough.
Is just me, guys, or y'all see this?
So she froze.
My computer,
Oh,
she
okay.
knows it.
Sorry. Just want to make sure my phone is good.
he's
Hey,
like,
Jocelyn.
what was the question that you had? I forgot. Sorry.
Jocelyn, on this session about the feeling, you say we will talk about it later. I'm just waiting until we're done with the PowerPoint so we can go over that.
Okay, what
The
is
feeling,
it?
the feeling, the ejection. I don't know anything about those two. I don't want to interrupt it, but when she's done with the PowerPoint, and then we'll go over this.
Yeah, that's fine.
All right, thank you.
Is she back or no? She's
No.
probably plugging in. So what's going on? The feeling of the ventricle, what it is, it's the atria is contracting, the ventricle is filling. So ejection is the ventricle is completely full, closes the AV valve, and then ejection is when it's leaving the ventricle, going up to the aorta or like pulmonary.
Wait, okay, that's like it sounds like a perfect explanation, but I'm gonna bother you for one big or little thing. Do you have this in writing?
What do you mean if I have this in writing?
I mean, if you have this in writing, or I had to take my notebook and then start writing what you just say. I just don't want to forget it.
Okay.
I mean, if you have those on your note, just like the way you explained to me, that's what I meant.
Let me see. Oh, I thought like you were saying to believe you have that on writing. I'm like, please don't believe me.
No. If you have like the same explanation you give me on your notes, or I'm gonna ask you to repeat it so I can write it down.
No, that's fine. Are you in the Miami group chat?
Yes.
Okay, so what I'm gonna do tonight when we're done before going to sleep, if I forget for some reason, don't worry. Tomorrow morning I'll send the notes to you, and then you'll have it.
Lovely. If you want to send it to the group chat, that's fine.
I don't think you're in the Miami group chat. You're in the Fort Lauderdale group chat.
Or me?
Yeah, is that's what she's.
I don't understand it like that. They have a one for Miami?
I suppose so. I just want to make sure that you're going to get the information because if you're not part of the Miami group chat, I don't want you to
I'm
like
not. I'm
wait
not.
for
I'm sorry.
information and then it's just not going to get there.
Wait,
I
she's
just
in
want to make
Miami?
sure.
What group chat is the one that? Which group is that? Fort Lauderdale?
Yeah, I guess
I think you recently add last week, right? Mindy?
Yeah.
Is
Or
that
the
the one
Fort one?
you're talking about? I didn't know if you have a separate Miami. Never mind. I think I'm just okay.
No, that's fine.
I'm just gonna shut up.
So what? No, you're good. What's your number? So I have it here.
Up to 786 372
Okay.
2301.
01. 786-372-2301.
Yes.
Okay, so either I probably send it to you tonight, or if not, probably tomorrow because I'm gonna be
Take
tired.
your time.
I
I
promise.
see you tired. Take your time. Whenever you send it, that's fine. I appreciate that. Thank you.
Okay, no problem.
All right. Thanks.
All right, I'm back, guys. I know my Wi-Fi died.
Welcome back.
So I used my hotspot, which some of you know, and my phone died. It was like on 20%. Like, how are you gonna die on 20%? Anyways, whatever. So let's go back to
I have a quick question that's not related to what we're talking about.
Okay, go for it.
So, oh crap, I just lost it. Hold on. Okay, so regarding like pressure within the ventricles and like when it rises above the pressure in the atria. So when the ventricles begin to contract, it raises pressure within the ventricles, correct? So,
Well,
like,
it's more, yes, but it's yes.
okay, so contract is like equivalent to pressure, right?
Yeah.
Okay, so then when does the ventricular pressure rise above the pressure in the atria? Like, is that when the blood is flowing into the atria where the ventricular pressure is higher?
Well, it's after the atria contract. Once the atria contract, all the blood's out, and if it doesn't contract, it really doesn't matter because the ventricle, so the atria will drop below once it loses all the blood in it.
Okay.
And then it will go below the ventricles, the AV valve will shut, and then the ventricles will start to initiate contraction, and then that will start
increased pressure and volume.
The volume in the ventricles at that point, once the AV valve closes, is the most that the ventricles, like the most volume the ventricles are going to have.
Right. Okay. So I just wanted to, okay. Just making sure. Okay. I just wanted to get the cardiac, like that part correct. I always get confused with like the pressure and stuff.
Yeah, I get you. I lost someone. We had 12 people. There was somebody left. Somebody was like, I guess it's over. Like, peace out, guys. Did you guys get kicked off? I don't think so. It's just kind of, yeah. Anyways, I don't know what I'm doing. You guys see all the freaking stuff for the paper? Isn't that beautiful? I know. So nice. All right, so a lot of this is going to be stuff that she didn't go over. So she didn't go over this. She didn't really go over that, but she did go over this. So defibrillation, when you have the shock, the shock things, when you go like VTAC, they be like VFib, and then they're like shock is 250, whatever. If you haven't seen Grey's Anatomy, please watch it. That's great. Anyways, so once they shock, it basically depolarizes all the cells at the same time and resets it, and all cells enter the absolute refractory period, because before it was like stopping the refractory period and the circus conduction ceases, where it goes like around and around and around, right, and keeps repolarizing, and it basically can reinitiate the normal rhythm. But it doesn't fix everything because there's still a problem. Like, there's still a problem. Like, either there's ischemia, there's dead somewhere, the heart, the SA nodes, it needs a new pacemaker, like whatever, something's wrong. So it just buys time. It doesn't really save someone for the long term. All right. So she doesn't talk about this at all. But she did kind of talk about this, so we'll talk about this. Okay, so right here, sinus bradycardia. You can see that there's a little, it's very, very small, but there's a very little atrial depolarization, right? But it's very slow, very apart from one another, right? So that could be from like the SA node. I mean, the SA node's working, obviously you can see, right? But it might be because this person's a runner, right? And they run marathons, and they're just like super healthy. So they don't need a faster heart rate or a faster, You know what I'm saying. They don't need that. Okay. All right. Ventricular tachycardia. This is horrible. We don't like this because it can turn into that, because it's showing you that that it's continuously contracting and it's not stopping contracting. It's really bad, and that's usually when the doctor comes over and it's like, VTAC, everyone get the paddles or whatever, and you know that scene. Anyways, so that's that. I don't know anything. I'm just trying. Okay, and sinus tachycardia is right here, and you can see that there's clear, it's clear heart rate, 1, 2, 3, and it could be, from any number of things. And one that's an ectopic foci, but one that's like sends rapid excitatory, pulses through the electrical current, that kind of stuff. I know you guys are so excited. And we don't need to know this, so we're just gonna move on. All right. Oh, well, I'm not in the other one, but basically this would show atrial fibrillation because of the fact you can see that there's like just a bunch of little things here, and it's just like all over the place, right? And that signifies like the P wave, and the P wave, is the atrial defibrillation and all that stuff. So if that's not working, then it's okay, but for long periods of time, like that kind of looks a little wonky, even the ventricular, anyways, it just looks wonky. So I don't think we want that either. But yeah, apparently you can live with it, right? I think so. That's the one you can live with. So, all right. Well, we finished this set. So what do you want to go to the next one, which is the cardiac output? All right. All right. So basically the cardiac output, left output equals right output. You can't have, differential because it could be better. But
Heart failure.
yeah, so it can, just like Jack Saint said, it signifies heart failure. The average heart rate is about 70. Stroke volume is about 70 mils. That's nice. That's even. I like that. It's very complete, very complete. But how you get the cardiac output is heart rate times stroke volume. So she says it's 5 liters, but she also said it's technically 4.9 liters, because if you times 7 times 7, 49 plus, math whiz here. But so that's how you get the cardiac output. And stroke volume, what is stroke volume?
The stroke volume is what's
The amount of blood rejected by the ventricle.
Yes.
You got this. You got it.
I'm trying.
And he got it.
Oh
no.
Yeah. Jack Saint's the one. He's getting straight A's right now. I know it. I can feel it in my bones.
Only if you know stuff. Let's keep going.
Okay. So the stroke volume is the amount of blood that's ejected by the ventricles. Okay. And so that's what it's talking about when it's talking about that. And how do you get stroke volume? So how you get stroke volume is end diastolic volume subtract by end systolic volume. And we're going to get to the chart, and I'm going to talk about that again. But the end systolic volume is the amount of blood once the ventricles are fully filled by the atria after the atrial contraction, if the atria contract, And the end systolic volume is the amount of blood left after ejection of the stroke volume. So if you subtracted the end diastolic volume and the end systolic volume, you would get the stroke volume, because it doesn't like disappear. It doesn't go, phew, we're gonna go somewhere else, It doesn't do that. But like, I had a question, like, what happens like to the blood from like, I'm guessing it would be different. Like, what I'm talking about, like with the heart, the arteries, like the right carotid, like what happens there? Does it like the blood? I don't know. maybe I'm just tripping. Like, does it go? Because it doesn't go from the aorta. It doesn't come from the aorta. It comes from the. I don't know. I don't know. Maybe I'm just tripping. I'm overthinking. We should stop thinking. So this is what's talking about. Cardiac output must meet demands for rigorous exercise would be 21 liters per minute, which is crazy when you're talking about the average is 4.9 or 5 liters. Like, that's crazy. So how you find out the maximum, so the cardiac reserve, the cardiac output max minus the rest is your cardiac reserve. So if, like, let's just say your maximum is 21 liters and your rest is 5 liters, what would be your cardiac reserve? Do you think? It would be like, I can't subtract, but it'd be about 16 liters as your cardiac reserve. Because,
Like, guys, are you guys there?
yeah.
Oh no, I'm talking about the team because I don't hear them when you ask the question. I just want to make sure they don't fall asleep.
We're here with. Wow.
Oh
I feel
my
the shake.
Oh
Sorry,
my
y'all. I don't know the question. I don't know the answer. That's why I don't say anything. But I was hoping someone say, "Oh, I don't know," you know, stuff
We're
like
all
that.
like brain dead, so.
Yeah, I think we're all.
No, I do understand. I am too.
Jackson, I
I
love
just don't
you.
want her to feel alone. Okay.
I love you. Oh my gosh, that's hilarious. Okay. All right. So in severe heart disease, this is one that really modifies the cardiac reserve because it can get really hard for people with heart disease to like do simple tasks because it's hard for them to like their heart to even pump and that stuff. So little to no cardiac reserve because they can't exercise, they can't pump more blood through their body, they can barely pump the blood they already have. So they're limited exercise tolerance. All right, this is fun. This is fun, guys. So it's just showing you like all the different things. Lovely, love that. Chronotopic, great. Yeah,
I think Jocelyn passed out.
yeah, we're that one's like, yeah, bro. Gonna go get something to eat, gonna get a glass of wine. We're on goals. Okay. I want some. Anyways, so newborns have a faster heart rate. Normal adults, females, that's their normal heart rate, and then males have a lower heart rate because whatever. They have they're just better. I'm just trying to say it. I'm sorry. Diana's like, what the hell did you say?
Women are superior. I cease to believe that men are better than us. I'm sorry.
They're not. We can do it better. Our heart
Yes, there you go. That's what it is.
Our heart beats faster and we live longer. So
remember, I'm here, okay? The only men here don't suck. Oh no, Nelly, she's there, but
I was gonna say you're gonna activate Jack Saint and then you're gonna
No.
activate me if you activate
I
him.
know. That's why I stopped. I see you there. I'm like, okay.
I gotta check myself. Gotta get back.
Let's keep moving, yo.
Okay, so there's a whole bunch of things there, and I don't think that you guys you know this. Like, you know this for the most part. I mean, it's just memorization. So chronotropic agents, but effectors of heart rate. So yay.
Yeah, that affect the heart rate.
Intrinsic rate of the essay notes about 100 beats per minute. She talks about intrinsic rate. She did on one slide in the nervous system, so the heart can beat by itself, right, by the SA node, but the PNS and the SNS have they have domain over it, so they modulate it, and so we talked about this before, the non-epinephrine and epinephrine, they make the heart rate beat faster, and acetylcholine makes it beat slower. And the rate is controlled by the pacemaker potential and the cells of the SA node, which are called the nodal cells. Yeah, they're called the nodal cells.
Pacemaker.
They're called the nodal cells, and the autonomic nervous system will affect the nodal, the phase 4, and they'll, depolarize it either faster or slower, depending on, to get it to threshold.
I didn't leave, guys. I just looked at my cameras in my house and I found a bunny giving birth in my yard. So I just run over there to close it out because my dog will eat the bunny. So I'm like just save it.
Again, Jocelyn? Again?
Yeah, this is the second time. Like you can't see it because it's really dark. But it's like there. Like
this has happened before already.
Yeah, before they just come to my yard and give birth to like bunnies. Hey, I have to
I've ever heard anything like that.
This is the second time. I heard it for the first time.
So random. That's so funny.
I know.
I'm always to my yard. Like they don't go anywhere, but they know. I think they automatically know that I'm gonna cover, and then nobody's gonna have access. Like not even the people that are gonna clean.
They know you're gonna protect them.
Yeah,
that's cute.
Really cute. Okay.
Sorry.
So showing you what it's okay. I was enthralled by your story. I have never in my life ever had two, I don't know, separate occasions where bunnies have came and gave birth on my lawn. Anyways, okay. All right. So this is basically showing you that the different, effects of the parasympathetic and the sympathetic nervous system have on the nodal cells. So the parasympathetic division is dominant at rest, and the sympathetic nervous system has a small influence in rest, and the rate depends on the activity or dominance of each system, which is coordinated by the cardiac center in the medulla. Is it the adrenal medulla? Like where is this medulla? What is we don't know. Was anyone?
It's gonna be the medulla and the heart.
Okay. I don't know. I don't know. Do you know where it is? Like located? Like does it have like?
You've got the medulla oblongata in your brain, and so the medulla oblongata is going to regulate heart rate, temperature, things like that. So
breathing. I got you, Emily. Oh my gosh.
When that gets severed, that's why you immediately die. Like when you get severed here, like if you were to fall back and hit the back of your head and you were to hit that area, you would just immediately die because your heart rate would just stop, breathing, respiratory, all of that would just stop completely.
That's yeah, that's horrible, but I remember because okay, Morgan does too. She doesn't lie because my professor, my AP1 professor, loved that word so much he would repeat it 80 times. He talked about it constantly.
Shout out to Dr. Gallo. I miss him.
Scott song too, the name and everything.
Yeah, they loved it. I was really weird. They had some kind of fascination with the medulla oblongata. Maybe they were mesmerized. I don't know.
Yeah, it's the name, oblongata.
So this is showing you the ugliest thing on the planet. We're not even going to talk about it, but okay. She did say this. The vagal simulation, that's for the parasympathetic. So if it says vagal or vagal, whatever the hell it's called or whatever, that would be for the parasympathetic division. Okay, so if you ever see that, think that. Don't know what this is doing. I did not understand, but okay. So cardiac output peaks with a rate between 60 and 80 beats per minute. Okay, because you cannot get any more blood. You cannot pump it because she basically explained that it shortens the amount of time in which the rest time, the diastole. So because that rest shortens, the ventricles cannot fill as much as they could, like, they just don't fill as much because it's just shortening that time more and more to allow for contraction and that kind of stuff. And heart rate can exceed 200 beats per minute. So there's this thing called the orange theory, and I don't know, but they say something like about like beats per minute, like measuring your like max heart rate and all that stuff. And they say like you need to get in that max to like get your best workout. Well, maybe not, because you can get it like through 160, 180 right there. It says it right there. I don't know. Just saying. I don't know. But, so just showing you right here that as you go up, it levels off at a certain percent, because, and then it goes down because once it gets so fast, it can't fill the ventricles with blood. Oh, look at that. Beautiful. I was studying, guys. Look at that. So I talked about this before earlier tonight. So the end diastolic volume is the most that the ventricles can fill after the AV valve closes. This is also called preload. Okay, and preload is directly, well, there's this thing called Frank-Starling law, which are two separate people, she said, and that the stroke volume is directly proportional to preload. Okay, so like you can kind of like, it's directly proportional. So if you had to like solve it, you know, you could solve it if you needed to, because if the stroke load is this much will be ejected, and then the rest would be the afterload. Well, no, the afterload would be, or how she explained it, is the stroke volume. So she said TPR. What does that mean? Does anyone know? It says TPR. Well, anyways, so the stroke volume means afterload. So after the ventricles.
Sorry, TPR is total peripheral resistance.
Interesting. So I'm guessing it's the amount of blood that meets resistance by the systemic system. But afterload is basically the stroke volume, the amount of blood that's sent into the systemic system. So it's directly proportional to preload. There we go. And then contractility. So we go to talk about that. So right here, preload volume coming into the ventricles and diastolic pressure. So there's that. And then the afterload resistance, left ventricle must overcome to circulate blood. So it pumps the blood through the aortic semilunar valve into the aortic, and it must overcome the pressure of that system so that it can pump the blood into that system. And that's called the afterload. So this is showing you a little picture of it. Okay. So the stroke volume, the preload equals the diastolic volume, and then the stroke volume would be the afterload. And so right here it says the what does VR mean? VR? VR? You don't know?
Ventricular relaxation.
Okay, so ventricular relaxation, diastole, and then the atria contract and pushes the rest of the blood into the bottle, right? Or the water. Then the amount of blood or water in the bottle after the ventricles or the atria contract would be the end diastolic volume, or the preload. Once the ventricles pressure, or the ventricle pressure supersedes or is more so than the aortic pressure, the semilunar valve will open, and the blood that is expelled is called the afterload, or the stroke volume. Mm-hmm. And the amount of blood that's left after the semilunar valve closes is called the end systolic volume.
Wait, can you repeat that again? I'm sorry, that last part.
We can try, okay? Every time I do this again, I'm like, maybe I forget, okay? All right, so we're going to say that this is the atria contracting, right, and pushing the rest of the blood into the water bottle or the ventricle, right?
Yeah.
And the ventricle is going to take the blood, right? And this is called it's going to take the blood in, right? And then the next step would be after the AV valve closes, then it would be called the end diastolic volume. And in the end diastolic volume, this is also called the preload. The preload is when basically it's kind of like contracting so that it can have more force, right? And once the pressure surpasses the pressure of the aortic or the systemic system, then the aortic semilunar valve will open and the blood will be expelled into the systemic system, and this is called the stroke volume or the afterload. And then, or the amount of pressure, I'm guessing, is the afterload. Do we know? I don't know. We should ask her. Someone should ask her. I'm sorry?
I don't
Yeah, we
think
could
I think it's like
After-
actual blood.
Because it points to the the squeezing of the bottle out of the blood out of the bottle. So yeah, I think it is that. I think it's the squeezing or the resistance of the blood into the systemic circuit.
Let me see.
Someone should look it up.
Initial stretching of the cardiac myocytes prior to contraction. It's the physical stretching of the cardiac myocytes, the muscle cells.
Okay.
That's preload.
Oh, that's pretty good.
Afterload is the pressure that the heart must work against to eject blood during systole.
So preload is the initial stretching of the cardiac myocytes. Afterload is the force against which the heart has to contract to eject the blood.
Perfect. Okay. Thank you. I knew I was wrong. I thought I was wrong. I felt it.
You're right. It's just the pressure that you need to eject the blood. So
Afterload is going to be the load or the pressure, and then preload is just going to be the initial stretching of the cardiac myocytes.
Okay. All right. Perfect. You guys said it perfectly. I will never remember. I'm gonna watch it again. I'll watch this, and then I'll be like, "Oh, they taught me. That's beautiful." Yep. And then after,
Is
sorry.
Number 4, is that going to be end of systolic volume?
Yep.
Okay. All right.
Emily's got this, bro. She can write the test right now. No. No. I'm sorry. No. Not my job. All right. So this is just showing you that the end diastolic volume is directly proportional to the stroke volume, or the stretch of the ventricles of the myocytes when at the end of the endosolic, indicated by the ventricular end diastolic volume. The stretch of the initial stretch is directly proportional to the force of the myocytes to push the blood out of the ventricle into the systemic circuit. Can someone repeat that so I can write it down? Maybe, possibly. Write it in orange.
repeating what, like the stretch indicates?
Yeah, the stretch initiate the stretch. The initial stretch of the myocytes in response to the end diastolic volume is directly proportional to the force when the blood is expelled by the ventricles into the systemic circuit.
Yeah, I can.
Or systemic, yeah.
I really can repeat that.
Okay, I'll try. I'm just gonna write it. It'll take me a minute.
You could just write that basically it's just like the pressure that fills up. Actually, I want to put it like better for you. Hold on. I'll say it better.
Write it in the
Say
chat.
filling is the filling pressure of the heart at end of diastole. And that's going to be like in terms of like the atria. The filling pressure of the heart at end of diastole. So the atrial pressure at the end of diastole determines the preload. Greater the preload, greater the volume of blood in the heart at end of diastole. And then afterload is going to be the force or load against which the heart has to contract to eject the blood. Yeah.
Yeah, my brain is not ready for this right now.
Yeah, my brain is.
I'm sorry.
Bloop, bye. Have fun.
Then afterload is the pressure against which the heart has to work to eject the blood. Pressure against. Yeah. That's confusing.
You tell me. Oh my gosh. Holy mackerel. The afterload is the pressure
Against which the heart has to work to eject the blood. Yeah. Awful. Just awful.
my nice orange color pencil. Okay. All right. So the stretch indicated by the amount of blood located in the ventricles of the end diastolic volume is directly corresponding to the force in which the blood is expelled by the ventricles in the pressure in which it has to forcibly go against the other pressure in the aortic system. Yeah. Systemic system. Sort of, maybe kind of. I'll only have to listen to that 800 million times again. Okay, so this increased end diastolic volume would increase also the stroke volume correspondingly, which if we hooked up, she said if you hooked up the heart, then you could definitely see this, that if the end diastolic volume or the volume at the end of atrial contraction would be directly corresponding to the stroke volume, where the amount of blood is expended by the ventricles. So this requires a stretch, right? The stretch of the ventricle and contraction of the ventricle stretch. You know, the greater the stretch to expound, or the greater the afterload, right? This to stretch, to expand, to push the blood along into the systemic circuit.
Yeah, and did she say all the time you think about stretch, think about contraction?
So the larger the end diastolic volume, the larger the stroke volume, and the stronger the contraction. If it's just corresponding, right? Yeah.
Olivia, can you explain end of systolic volume? Because I have stroke volume, I've got end of diastolic volume, but I don't have systolic.
So end systolic volume is once the semilunar valves close after ejection of the blood into the systemic circuit, the blood that is left over in the ventricles after ejecting all its blood out, that's the end systolic volume.
Oh, okay. That's easy. Okay. That could be either on the left or right. Like this is all either left or right.
It's all on the left or right, but I'm pretty sure that all our questions are going to be on the
left.
The left.
Yeah, because they said it's regarding the left. Okay. Got it.
So right here, so in a failing heart, it's really wonky and really messed up, and this doesn't apply. Frank Sterling law only applies to healthy people.
Okay.
And so, just like Jack Saint said, you can directly correlate stretch to contraction. So, if the greater the stretch, the more forceful the contraction. Basically, if the more the blood, the greater the contraction, and so on and so forth. They're directly proportional. The stretch of the ventricle will maximize cross-bridge interactions, which means like the actin and the myosin. And because it maximizes them, then it lines them up perfectly, then the stronger or greater the force of contraction, and this will allow the more blood to be expelled into the aorta via the semilunar valve into the aorta and all that stuff.
This is where we left off, right?
Yeah. Yep. There's only 38 ones.
Isn't it beautiful for how you said it's just 38?
Well, we're on 20, so there's only 18 left, and then death. I don't know.
Yeah. She says like whatever we're covering right now on the next one, it's gonna be on the test. So I hope they just leave it there. I know she's gonna want probably to give more for like content for the classes, but I just hope she leaves it there because then we're gonna be overall confused.
I think
It's all gonna be on cardiac output, she said.
And we don't still won't know what's gonna happen with anatomy yet, since Dr. Shang quit. I don't know how they're gonna do it.
I can't believe that happened.
I think she said burial. Well, from the email that I read, Dr. Chen said, I think she mentioned Dr. Bear will do the respiratory system for anatomy.
Yeah, but when we spoke to Dr. Lyons, she said that she was going to tell Dr. Barry Hill not to put respiratory on the exam.
So you're gonna be only on blood vessels?
Exactly, like that's what she wants.
Oh my gosh, that's horrible.
Wait, so she's saying
That will be easy.
That'd be easier though, because then you could just
Because
concentrate.
we have to concentrate on one thing. So like
But
that will
she's
be late.
gonna try that it's not on her. Like it's not her saying. She's just gonna say, "Hey, they've been through a lot, changing so many professors,
Mm-hmm.
and like, can we give them a break?" But she says it's not on her. Like if she wants to put it, at least she's gonna try.
I still don't know what we're supposed to study on blood vessel because she skips so many slides. So I don't even know.
It's not too bad because I'm gonna do a Kahoot for next week for that. The blood vessels and stuff.
Oh, that's gonna be my first one. I'm so ready.
So I'll do one on that, and then I'll listen to her lecture again from last week, and I'll just emphasize everything that she said. And it shouldn't be too. I mean, we did a lot of blood vessel questions on the last test, so that's kind of what I remember. So it's not too horrible.
No, it's not. Definitely not. It's literally all memorization.
Yeah.
Where do you find this sheet?
Huh? Oh, okay. So if you go to your modules and then you go to I think it's week 8, sorry.
There are so many questions on here.
It's not that bad. Don't get scared or intimidated. If we don't get through it tonight, we have it depends how late you want to stay up. Last week we stayed up till 12:30. So
I'm just freaking out because of this paper. I haven't even started. Don't even know what I'm gonna write about yet.
Me too.
I can't find freaking articles on anything.
Me
I
too.
haven't heard either. Like nothing.
Don't even mention that
I'm like,
part.
what am I
because
gonna
that's gonna
do?
get me upset.
You're not alone.
You're not alone.
Okay,
You're
good.
not
Because I
alone.
felt like I'm like, oh my god, I'm probably the only one. I see
No.
Olivia.
The only one. Hey, mama.
you saw my paper. I feel bad. I'm sorry.
Yeah, screw you for being a good student. I procrastinate.
I didn't procrastinate. I just didn't know we had the paper.
I didn't even do it until Monday. Is this procrastinating?
No, definitely not. I feel
No,
you.
procrastinated is not
feel
last
you.
minute. It's too complicated. If you
It's
just
very
like pull
weird.
up a story, like, but we can use any sources to look for the article, right? Like the GOV, CDC, stuff like
All
that. No.
sources, it has to be peer reviewed.
Yeah, just like we did for the first class, right?
Yeah.
It could be past 5 years this time.
Been trying to look on Cinol, like from the school, and I can't find anything.
They don't have a lot of information on those things.
What
no,
I,
they
okay,
don't.
so let me give some pro tips, guys. Okay, so what I did, well, what you can do. So I looked it up on the regular web, okay, and then I cross-referenced with Cinol. So I put the titles of the ones that I thought were good in Cinol, and it came up with a full text. But for some reason, it like back shuffles them. I don't know why, but I found the titles that I needed. You can also go on, so you log into your Shark Link and then go to Google Scholar. Let's see if I can do it right now. Let's see if, because I used to do it with Palm Beach State all the time. Let's see if I can do it now. Okay, Shark Link. Oh, well, that's beautiful. I like that. Love that. See if it keep. No, it login failed. Apparently, I'm not the same person. Maybe it doesn't.
Libraries.
Oh, I like how it's all in caps. That's beautiful. So I go on Google Scholar. Look in there. What's the topic? Clara. I did Clara Barton. What do you want to do?
Florence Nightingale.
Nightingale.
She probably has the most stuff, to be
I
honest.
know. That's why I was so like surprised that when I went on Cinol, like through like the libraries, I couldn't find anything.
It was so hard. There's nothing.
Like, what the hell? Like, she's like the most popular nurse. Like, what is going on?
Legit, she's a ghost. I was like,
Gross.
I was like, everything was like celebrating. I'm like, no, I don't want to celebrate her. I just
No,
want
literally, that's all I saw. And then I clicked on the article and like this old man popped up. Did that happen to you? He's like, I was like, what is this?
I was like, can't somebody just tell me where she was born? And like, I was
I
literally,
know, I was trying to get like background information on her and nothing was popping up.
I was like, it's only Wikipedia. Everything was like celebrating Florence Nightingale.
That's so funny because the same things were popping up for me.
Like, I don't want to celebrate her.
Okay.
I know that's really bad for me to say, but I really didn't know who she was.
I heard her name, but I didn't know exactly what she
Yeah, me too. I didn't know.
When the professor said Florence, I just thought about Italy. So I was like, some other place.
Close.
I'm like, no.
Someone
So
should pause the
I'm right.
recording while we're doing this.
Yeah. Do you want to pause?
Pause the recording? Okay.
Yeah.
I literally put in the group chat. I was like, and I. We're usually so good about that. It's okay.
No, I'm actually pretty horrible. Let's move on. Okay. One of the factors that controls the force of the heart contraction is the A, initial length preload of cardiac muscle fibers, B, number of intercalated discs in the cardiac muscle fibers, C, number of gap junctions between the cardiac muscle fibers, D, the degree of depolarization in the SA node, E, the length of the His bundle. Okay, take a minute. Okay, before you say a word, just take a minute. I need to read it. Okay. No, yeah.
We talk about it. Like
I think
answer.
I got it.
It's not gonna be the preload because it has to be then the other one. What's the other one?
The afterload.
The afterload is the one that has to do with the force.
I don't remember her saying anything about intercalated discs.
I think it'd be A, to be honest.
But why did you say the initial length, the preload?
The pressure.
Because the prelude has to do with the strength. the strength of the cardiac fibers.
The load, yeah, one of the factors that controls the force of
It
heart.
could be
It's
because
A.
the more that you get, the more you're gonna eject. So that's, yeah, you're right.
It's A.
All right, my ladies.
It's A?
He's
Yeah,
out.
I think so. Are you gonna leave?
All
Yeah.
right, my ladies. I
Your
can't
ladies?
finish with
I
y'all.
ain't your lady.
Yeah, I cannot finish with y'all tonight. I'm passing out.
It's okay.
Good night.
I'm gonna have to let you
Sweet
go,
dreams.
guys.
Now we could say that women were stronger. I'm
I
sorry.
know, yo.
Oh
No,
my God.
actually, I'm not gonna say women are stronger. I'm gonna say women are smarter. Y'all are
Yeah.
smarter than men.
No, you're
That
not.
100%. Cause y'all
Yeah.
been killing it, and keep doing it, guys. I'll see you guys tomorrow
Tomorrow.
See you
and
tomorrow.
Thursday. I promise. I'll drink some caffeine for
I promise.
Thursday. For next Thursday.
You
'Cause,
probably worked hard today. Sleep.
Yeah.
yeah, I will. I'll get some sleep. Good night, guys.
Good
Good
night.
All right.
Okay.
I don't know what ionotropism means. I've never seen that in my life. I'm sorry.
Okay. Well, so positive, she spelled it wrong, but ionotropism refers to
Can I look at my notes? I
Did
remember
we
I
talk
wrote it
about
down.
that today?
it's B.
What is ionotrop? No.
Movement of blood elements related to chemical change, change in a chemical gradient.
That's because it'd be ionotropic, so I guess it could be.
Oh, ionotropic.
I don't know. Someone look it up. Wait,
It's
on the
D.
internet.
Oh.
It's D.
Mm-hmm.
D,
D as in dog.
increase contractile of the heart.
Hold on. I think I wrote this in my notes.
No, you did not. Don't even.
What?
I don't believe you. I
I
don't
think
remember.
I remember writing something about this. So let me
No,
check.
I don't remember anything about that. Like at least I don't have anything.
Was
I followed you back. You have 2,000 followers.
Who?
what I'm saying.
Jocelyn.
Listen, that's nothing. I don't have any.
Nothing, bro. Compared to my 150.
I'm not gonna put someone on the spot. I'm looking at her. She has like many followers. Please share my page.
150.
Sadie.
Oh.
She's like there.
Yeah, but that was because I used to do network
Yeah,
marketing.
I had the same. Like I had a lot, like bunch of followers, and then I had to delete my page for unusual reasons. And then I had to open it again, and I didn't know I could just like probably have it locked out for. So I'm getting back there.
But you have a lot.
Oh, I think
Let's
she.
hear you. I'm stalking you.
Do you find it?
Oh no, she never talked about it because it was it's drugs. It does deal with drugs.
Okay. We nurses, we don't do drugs. We're good. That means we
No.
don't have to go
So
over.
this question we don't need.
Yeah, we don't need. Like we don't deal with that.
No, she like literally said like she just cut it out. I'm pretty sure.
Oh, okay. Never
Like,
mind. I thought I had it somewhere, but it was something different. It was chronotropic agents.
Yeah.
That's what I was thinking of.
Why?
I remember her saying agents that raise heart rate are positive and agents that lower heart rate are negative, like acetylcholine and epinephrine. But
what happened with 7?
Bro, we don't know. 7's gone.
Yeah, it's like that.
The effect of the parasympathetic nervous stimulation on the heart is A, slowing of the heart. Yes, it's A.
Yeah, it's so
Okay.
dark.
It's A, yeah, because it's.
It has to be.
it is.
Yeah.
I just felt like we all knew that. I don't know.
Even I knew that, and I don't know anything right now.
You do know, girl. Oh, I don't know about this one. Let's see.
The P wave of the normal EKG is associated with the aortic notch, an increase of atrial pressure, atrial contraction, ventricular contraction, or none of the above. I think
It's gonna be atrial
Contraction.
Contraction.
Yes, it's atrial contraction.
Supposed to be depolarization, but
Yeah, but hey, when it's not there, it's
Well,
contraction.
it's associated.
yeah, it's
It's
associated.
associated with, like, it's gonna contract the atrium. Okay, okay.
It says note that it strictly represents only atrial depolarization, but since the question says associated with, then C is correct. The P wave does not represent contraction directly though.
Beautiful.
That's actually something it said.
Yep.
Oh, would you look at that?
It said it on the bottom of the question.
How many questions do we have?
A
Depolarization,
lot.
not that hard. Like, why don't they
There are
just
a lot of questions.
50?
Um, yeah, almost.
Do you guys want to do this another day or do it tonight?
That's gonna be a lot.
Maybe we could just do like half of them tonight or something. And then
Let's go, Lucas.
sorry. I don't even know anything.
what do you mean? You literally sat here and explained like a whole thing to me. You're like, I know nothing.
I just like
No, but
figured
like
it
I
out
think
to be
when
honest.
we explain, it's better because you're explaining at the same time you're learning.
I just
I wish.
I'm looking at these questions and I'm not too sure.
Yeah, look how many questions there are.
No,
I don't know about this.
no, we need another live. Can we do another section eventually?
I
And
think
then-
we should maybe do like 5 more and then maybe this will be the first thing that we do. Maybe we could have one more session like before Thursday just because I feel like there's a lot. I
I
don't
think
know.
there's a lot of information on this.
Olivia is
this
not ready.
exam.
She's like, no,
I
I
second that
I saw her face. I saw it. I saw it.
Olivia,
think
let's
I'll
have
fix
another
it.
study
I saw it.
session before
It's like-
Thursday.
That.
She wasn't ready.
I don't think.
She wasn't ready. I'm telling you.
Jocelyn, don't call me out.
Hey, I saw your face and I just say it from you. Oh no, I wasn't ready.
Okay. Well.
Like the well.
Well,
Okay, we're starting in advance.
I mean,
I'll try. I'll see what time I can do it. We'll see.
It's just to finish this and then we just
No,
don't-
because like the thing is like people like they're used to like especially like the week before or like the week of the test like
we're gonna
there's
be
like
studying a lot.
25 people on here and like they all know like this like what's
No.
happening.
No.
But like then we have to like explain it again. That's the problem. It's like
We're recording. We're recording.
yeah,
yeah.
but like what am I supposed to be like? Nah, we recorded it.
So
like,
she
you
go,
know.
oh, you know
Yeah.
what we could do? Hey, she has with us a meeting on Saturday at what time was it, Mandy? I don't know if Mandy's here. Is it
Here I am. It's at 4.
at 4? We just go over at 4 with her and that's it. And then we're good. And that one's gonna be recorded and posted. Can we do that?
I
Well,
think
we're gonna have to go over it with the other people too.
no, you don't.
Yeah, you do.
Oh, you're recording. Oops.
Oh, okay.
That's what I'm trying to say, that you're recording.
Memory. Okay, moving on.
We'll go over it next time with them, everyone. Okay.
Next question.
Which of the following mechanisms? Oh, I can't talk.
I
Which
don't
of the
think no one is gonna be watching this for actually like the 3 or 4
That's
hours
not-
that
bro,
we
nobody watches this. Don't even lie. I look at the views and like,
You can see how many people view it.
yeah,
What is it like 5?
yeah.
I watched this.
You do? Oh my God. You watch
That's one of
Yes.
the 5s.
I don't watch it because I leave it.
That's what I'm saying. Like I want to be here and like in the moment instead of like, you know.
I'm blown away. You watch it? You watch me talk?
Mandy watched it.
First shift
Yeah,
at
she
work, I was
watches
listening
after
to
we
last-
finish. She really does. It's honest. Like she watches it again.
Yeah,
And she actually said that she really liked it and she learned a lot from
I
it.
did.
So
I'm gonna
it's
cry.
not-
Oh my
We should
God.
pay Olivia.
I know, right?
per hour.
That's great.
$1 per person.
No, don't be
$1.
How do you-
You'd make a whopping $6.
Oh, All I gotta say is nobody's allowed to come except the people that were there last time, and then you'd have like 17 people hit me up in my DMs like, "Hey, can I come?" Like seriously, that's all you have to do. If you wanted to do it, but you don't, just, but you just make it unavailable, and then everyone wants to do it. It's like
I'm gonna find it on Saturday. I'm gonna ask her, and then I'm just gonna highlight the answers that she says, and then if
no.
we have
She posted it. She posted the answers.
Oh, okay.
Which is
We're good.
yeah. Which of the following mechanisms is the most important for maintaining an increased blood flow to skeletal muscle during exercise? A, an increase in aortic pressure, an increase in aortic in mean pressure. C, a vasoconstriction of the splenic and renal areas. Just no. Anyways. And D, skeletal muscles vasodilation.
I don't know about this, but I would say
I would say D.
I'd say
A.
D.
D.
Wait, but if you're wait, maybe
I would say A and D. What the hell?
See, the
A and D too. I mean,
pressure has to do with more blood coming in because you're exercising, so you need more blood. But at the same time, muscle vasodilation isn't that like no, it's not that because it's not constriction.
it's not constriction though. Constriction, you
Yeah.
want to keep the blood deep in
So
the.
I would say A
Yeah.
and tell me which one it is.
Let me
Probably.
I think it's D.
It's
It's
D.
D.
Yeah.
Yeah.
Want to
No.
dilate the vessels so you can like cool yourself down, right? I think that's the reason.
No, but
That was
it's
like in the way beginning of when she talked about like temperature and everything, I believe, right? Is
but
that it?
I think this is more leaning towards making sure your skeletal muscles are getting enough blood flow so that your muscles can contract
Right.
more. Not so much
That's true.
if it was saying like how do somebody like keep their temperature normal while exercising,
Yeah, that's true.
muscle vessel like vasodilation to like cool off. So this one is more like trying to give blood to the
For
skeletal.
more contractions to happen. Got
Exactly.
it.
Yeah.
Now I know I don't know anything.
Oh my god.
Oh, you too. Don't even.
This confirmed it.
We just needed
Confirmed.
one question.
Confirmed.
Question confirmed it.
Wow.
All right. Which of the following events is represented on the EKG? Oh my gosh, this is the question. All right. SA node depolarization, AV node depolarization, his bundle depolarization, depolarization of the Bachman's bundle, atrial muscle depolarization.
A. I'm with the SA node depolarization.
A.
I don't think
I'm
so.
gonna say E.
I would say E too. Atrial
Yeah,
muscle. Yeah.
because
Yeah.
it doesn't show the
Yeah.
it doesn't show. It shows the area in which it's depolarizing. It does not show the.
ECG will tell you your nodes, but not an EKG.
Bro, really?
I thought they were the same thing.
I thought they were the same thing.
Yeah.
Really?
Yeah.
Are they?
They're
I
not the
don't
same.
know.
I don't
The
know.
same thing.
There.
No, they're the same thing.
Program?
Thank
Oh,
the
it's the same
Lord.
thing.
I thought it was the same thing. I'm so
It
good.
is.
It is.
Okay.
What's the answer?
So why was it atrial muscle depolarization?
Because it doesn't measure. It doesn't.
Oh, the atrial depolarization.
Because like
So
it doesn't show it doesn't show the SA node depolarization. It shows the area in which it's depolarizing.
Okay.
Muscle contraction.
Because I thought it would have been SA node depolarization.
No.
But that's just the specific area.
The SA
Yes, it's the
causes the
specific
electrical
area.
current for atrial depolarization.
Got it. Okay. At least I was on the right track.
You were on there. You were on the way.
I'm getting there.
Who else doesn't want to go to the first class tomorrow?
Oh, I'm driving an hour.
All right.
You're driving an hour?
Yeah.
Oh my god, why don't you just do it from Zoom?
Because I have a lot of questions to ask.
True.
Always.
Bro, I can't even ask questions in that class. I feel like I'm mocked.
I always ask like in break. Like whenever we're in break, I'm like, when-
Oh no, if we ask on break, they're like, this is our break too. Don't ask us questions. I'm like, oh, okay.
Really?
I had a problem last
Pretty
class.
sure it was them that asked. That
She
said
skipped
that.
the whole class.
Maybe
She-
it wasn't Newman and Connor, but Lang and Connor said that, I think, the first
Oh
class.
my gosh, that's
They're like, it's
horrible.
our break too. I'm like, okay.
You guys, Miami or Fort Lauderdale? Fort Lauderdale?
Fort Lauderdale.
Isn't that beautiful?
Yeah.
How many students in your class?
Look at Olivia.
Not that many.
No.
No?
Really, no. Yeah, no.
I used to go and now I'm just doing on Zoom unless for physiology exams, then I'll go into class.
I go
How
for
many
physiology.
students
I
you
go in the mornings on Mondays.
How many students y'all got in y'all program though?
107.
Holy
We have like 17, what? Or 16?
Yeah, we're like 18. Well, we're 18, we're
We're
17.
so tiny.
16.
16?
1-6.
Yeah.
Bro.
Okay, what campus are you at?
Fort
Myers.
Myers.
Oh my gosh.
Amazing.
Yeah.
Fort Myers 239.
Hi, Julie. You want to say hi? Come here.
A ver. I don't see anything.
Oh,
Ay, Dios mío. Is it a he or a she?
Joy. She's a girl.
What's her name?
Joy.
Hi, Joy.
Say hi.
she's so cute.
Oh, get away from my bunnies. I can't wait to see my
Oh, she loves you so much.
sister.
She's my baby girl. Are
Yeah.
you done? Okay, bye. Go lie down.
Are we
Alright.
gonna stop now or no?
We're gonna
Yeah, we're
okay, no, what I want to do, I do want to do something, but I do not want to do this.
okay. Thank you.
Okay, where's my friend?
No.
Front and center. Emily.
Oh no, I'm not doing that.
No.
Emily, come here. Come here.
Get it. Get it.
Emily.
What is it that you want to talk about? Okay, hey, I'm ready.
Ya te quité ya.
I'm ready.
Is Emily here? Did she leave us?
No, she left.
Oh, she's here. She just
Nah,
like,
she's right there. She's like, nah.
Try not to move, so she thinks you're like,
Wait.
frozen.
move. Try not to be
Like,
exactly.
nah,
Oh my God,
son.
so good. Oh, you lost.
Good.
Okay, all right. So let's go through this. I'm gonna explain it to Emily, all right? Okay, so no, I don't even like this one. Can I like go to the
I
other
was gonna say, why would you do that?
one? Not wrong one. There's like 8. Oh yes, okay. All right, so
And
we
that one's
have lots of lines and they're very complicated, but they're not that complicated. It's not that complicated, okay? So what I want you to look at, so right here, well, I first want to draw. Okay. Right here, this red line is the ventricles. Okay, so when you see the red line, that's what the ventricles are doing, and it's measuring the pressure in the ventricles. So as it goes up, the pressure will go up. Okay, this line right here is the atrial pressure. So the atria, okay? This line right up here is the aortic pressure. So when you're talking about, let's start over here because I like this, okay? Right here, the top line is the atria, and the atria are open, or the AV valve is open because the atria have more pressure in them than the ventricles. So it's open and the ventricles are filling with blood. Once they are pretty much filled and the SA node is firing, basically, and fires the first action potential, it depolarizes the area in which in the atria, this will contract. Do you see how it goes up a little bit? Because it's showing contraction of the atria. After the atria are contracted, then the ventricles will have, the pressure in the ventricles will go up. And right here, this is where the AV valve will slam shut. Ooh, look at that dramatic effect, will slam shut. And after this, it will be the end diastolic volume. Okay. The end diastolic volume is the most amount of volume that the ventricles have at the end of atrial contraction. Okay. So it's the most the ventricles will have. In this time right here, this is called the isovolumetric contraction phase. Okay, it's the preload, right? It's how it's stretching, right, to prepare it, how it initiates the stretching to prepare the ventricles for contraction. It's called preload.
Okay.
Once it reaches up here, right, this is where the semilunar, I'm not going to spell it all, SL. The semilunar valve opens because the aortic pressure is lower than the ventricle pressure. And this, as it's shooting off into the system, the pressure in which it's shooting off is called the afterload. Okay. And once it shoots off, then this is where this is called the ejection phase. Okay. And in the
Can I
ejection
interrupt for a
phase,
second? So
what?
I just want to make sure. So the afterload is the ejection phase?
No, it's the amount of pressure in which the blood is going into the systemic circuit.
So it's when the semilunar valve.
No, it's like the amount of pressure in which the blood is being shot into the systemic circuit.
Grab a bottle of water without the top and do like that. That's the pressure. It's coming out, but that's the pressure that you're putting into it.
Okay.
Okay. All right. So after this the blood is ejected, see how right here, how it's going down? Okay, it's still not below the aortic pressure. Once it gets to about right here, the semilunar valve will slam shut, which corresponds to the second heart sound. And this will start the isovolumetric relaxation phase of the ventricles, where the ventricles are starting to relax. Okay, and this is also called the end systolic volume. Once this door shuts and there's no more blood being expelled into the systemic circuit, that's the end systolic volume. And right here, this would be the end diastolic volume. Okay. After this phase, you see how the atria are rising in pressure? It's because the atria are filling with blood from the superior and inferior vena cava. Once it reaches to about here, the atrial pressure goes so low that it goes below the atria very slightly, and it starts to, and the AV valve opens, and that allows for the ventricles to fill with blood.
Beautiful.
Beautiful. Emily?
Emily, you gotta say beautiful.
What?
Isn't it beautiful?
Yeah.
Thank you. She said yeah.
I just if we're going like from left to right, we go from left to right, so we start all the way on the left, and that just like starts the beginning of everything, and then it just repeats itself and keeps repeating itself.
Yep, over and over and over again.
It's so crazy how all this happened so quick and we gotta learn all of it so slowly.
Literally.
Bro, this happens as
So
we're
quick.
talking. This weird throughout. This is happening constantly. Isn't that crazy?
I don't
remember every small little detail about it. It's just woo.
Woo.
Can we go over that one more time, maybe?
Yeah. All right.
I just get okay. Yeah, never mind. Let's just go through it. I don't need to talk about my feelings.
Question so I can emphasize.
No, I don't have any questions. I was just gonna say how frustrated I am. Let's not talk about it.
I mean,
let's go through it one more time.
We're all in this together once. I'm recording. Oh my gosh. Somebody could.
No one is gonna get this far in the recording, I promise you.
Ow.
I will.
Okay, well I meant like in the like people in the group chat when she sends this, they're not gonna.
No, they say thank you and then they never watch it. They probably click on it and then they're like, oh yeah, it's there. And
they're
then
like, wow, it's too long.
Bro, this is 4 hours? What were they doing for 4 hours? Jesus.
You could stop the recording because like we already know we're gonna keep on talking about the same thing.
Yeah.
Well, yeah, let's stop it.
Yeah.
Yeah, no one is gonna watch this part.